small magnet rests on a wooden table. Beside it lies an ordinary paperclip, barely shining under the room's light. You bring the magnet close, and in a quiet instant, the paperclip jumps upward and clings to it. The entire Earth, a planet with a mass of nearly 6 times 10 to the power of 24 kilograms, pulls downward on that same paperclip with all its gravitational might. Yet this tiny magnet, no heavier than a coin, effortlessly defeats the pull of the planet beneath your feet. That single motion, silent and almost unnoticeable, exposes one of the greatest mysteries in all of physics. Gravity is the architect of the cosmos. It shapes galaxies, bends light, and decides the fates of stars. It reaches across billions of light years, holding entire clusters of galaxies together in invisible webs. And yet, when compared to the other forces of nature, gravity is almost absurdly weak. The magnet and paperclip reveal this imbalance so perfectly that it almost feels like a trick. How can a force strong enough to anchor worlds be so powerless that a simple toy can overcome it? To understand the scale of this weakness, we have to compare gravity with the 3 other fundamental forces of the universe: electromagnetism, the strong nuclear force, and the weak nuclear force. These 4 forces govern everything that happens in nature, from the fusion at the core of a star to the decay of subatomic particles. They form the foundation of physical reality, and yet they could not be more different in strength. Consider electromagnetism first. The magnetic pull that lifted the paperclip is part of this force, the same one that powers lightning, allows atoms to hold together, and carries radio waves across space. 2 electrons placed close together repel each other through electromagnetic force. If you also calculate the gravitational attraction between them, the electromagnetic repulsion turns out to be roughly 10 to the power of 40 times stronger, 10 followed by 40 zeros. That is not just stronger, that is unimaginably stronger. If gravity and electromagnetism were boxers in a ring, gravity would not even make it to the fight. It would be crushed before the bell rang. The strong nuclear force, on the other hand, binds protons and neutrons within the atomic nucleus. It is the mightiest of all known forces, the one that overcomes the electromagnetic repulsion between positively charged protons and glues them together. Without it, atoms could not exist, and the matter of the universe would disperse into dust. This force is about 10 to the power of 38 times stronger than gravity. Again, the difference is so extreme it almost defies imagination. Then there is the weak nuclear force, responsible for radioactive decay and the processes that fuel the sunday. It is weaker than the strong force and weaker than electromagnetism, but even it surpasses gravity by roughly 10 to the power of 32. Gravity, it seems, finishes last in every comparison. And yet, gravity has something the others do not. It always attracts. Electromagnetic forces can cancel out because there are positive and negative charges. The nuclear forces fade away outside the nucleus. But gravity never reverses and never turns off. Every grain of dust, every planet, every star pulls on every other piece of matter in the universe. These countless tiny pulls add together, and across cosmic distances, their sum becomes enormous. Gravity wins not through strength, but through persistence. Imagine standing on a quiet plain at night, looking up at the Milky Way. Every star you see, and everyone you cannot see, is pulling on you. So are the planets, the gas clouds, and the invisible dark matter that surrounds them. The combined gravitational tug from all of it defines the structure of the cosmos. Galaxies orbit one another, stars circle their centers, and planets move in elegant ellipses because gravity keeps everything in harmony. But go smaller down to the scale of atoms and gravity fades into near nothingness. At that scale, the electromagnetic force rules. It dictates how electrons orbit nuclei, how atoms bond into molecules, how chemical reactions unfold. The gravitational attraction between 2 protons inside a nucleus is so small it can be ignored entirely in any calculation. It is as if gravity ceases to exist. This contrast is what makes gravity so fascinating. On the smallest scales, it is irrelevant. On the largest scales, it is the only thing that matters. It holds galaxies together, slows the expansion of the universe, and sculpts the vast cosmic web that stretches across space. Somehow, the weakest force becomes the master of everything we can see. The puzzle of gravity's weakness is one of the deepest questions in modern physics. Physicists have measured its strength with extraordinary precision, yet we still do not know why it is so small compared to the other forces. It is as if nature deliberately turned the dial for gravity almost all the way down. If that dial had been set even slightly higher, stars might burn too quickly, planets might never form, and life, as we know it, might be impossible. For now, we can measure gravity, we can describe its effects, and we can predict its pull, but we do not truly understand it. To uncover why gravity is so weak, we must first confront a more fundamental question. What is gravity itself? Gravity has always been both familiar and mysterious. Every person feels it from the moment they are born, yet few ever stop to think what it truly is. We experience its pull as weight, as the downward tug that anchors us to the ground. But that sensation does not tell us what gravity is made of. It only tells us what it does. For most of human history, that was enough. People accepted gravity as a fact of existence, an invisible hand pressing everything toward the earth. Then came Isaac Newton, who asked the question differently. Not what gravity feels like, but how it works. Newton realized that the same force that causes an apple to fall to the ground also holds the moon in its orbit. His law of universal gravitation changed everything. It stated that every mass in the universe attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It was a simple formula that could describe the motion of planets, moons, and even comets. With it, the heavens and the earth were united under one mathematical law. This was a breathtaking leap for its time. Newton did not explain what gravity was, only how it acted. He gave the universe a way to calculate attraction, but left the cause itself as a mystery. He once wrote that he made no hypothesis about what generated this force. Still, his law worked astonishingly well. For more than 2 centuries, it described everything from cannonball trajectories to the paths of planets with unmatched precision. But in the early 20th century, the picture changed again. Albert Einstein saw that Newton's theory, though powerful, could not explain all the observed phenomena. Mercury's orbit, for instance, deviated slightly from Newton's predictions. Einstein suspected that the very structure of space and time had something to do with it. After years of relentless thought, he proposed his general theory of relativity, a vision of gravity unlike anything before. According to Einstein, gravity is not a force in the traditional sense. It is the result of mass and energy curving the fabric of space and time itself. Imagine laying a heavy ball on a stretched rubber sheet. The sheet dips under the ball's weight, and smaller marbles placed nearby roll toward it. The marbles are not being pulled by an invisible thread. They are simply following the curved surface. In the same way, the sun bends the geometry of space around it, and the earth moves along that curved path. To us, that curved motion feels like a gravitational pull. This idea changed our understanding of the universe. Space and time were no longer passive stages where matter played out its drama. They were active participants, able to bend, stretch, and ripple. Massive objects could even send waves through this fabric, gravitational waves, ripples that travel at the speed of light. Einstein predicted them in 1915, and a century later, scientists at the Laser Interferometer Gravitational Wave Observatory detected them directly. 2 colliding black holes had sent tremors through the very structure of reality. Yet even Einstein's elegant theory does not explain why gravity is so weak. His equations show how curvature relates to mass and energy, but they do not tell us why the effect is so small compared to other forces. If space can be bent, why is it so hard to do so? Why does it take something as massive as a planet to make even the slightest dent in space-time, while a tiny electron can create an enormous electromagnetic field? These questions cut to the core of modern physics. The weakness of gravity is not just a matter of scale. It shapes everything about the cosmos. If gravity were even a little stronger, Stars would collapse faster and burn out before life could evolve. If it were weaker, the gas clouds in the early universe might never have condensed into stars at all. The delicate balance we live in seems to depend on this faint pull being precisely what it is. Physicists have tried to calculate the strength of gravity using fundamental constants of nature. The result defines something called the Planck scale, a limit beyond which our understanding of space and time breaks down. The gravitational constant, the speed of light, and Planck's constant together suggest that gravity becomes comparable in strength to the other forces, only at unimaginably high energies, far beyond what any experiment on Earth can reach. Between the scale of atoms and the Planck scale lies a vast desert of weakness. In that desert hides one of the greatest puzzles in science. Why is there such an enormous gulf between gravity's strength and the others? Some call it the hierarchy problem, the mismatch between the energy scales that govern gravity and those that govern the quantum forces. This problem is not merely academic. It challenges the dream of unifying all forces under a single framework, the long-sought theory of everything. For all our progress, we still live in the shadow of this mystery. Gravity bends light, warps time, and shapes galaxies, but at the quantum level, it all but disappears. The same equations that can predict the dance of planets fail to describe how gravity behaves among particles. To move forward, physics must bridge this divide, finding a language that unites the curvature of space-time with the quantum world of fields and probabilities. And yet, perhaps there is something deeper hidden in the weakness itself. Maybe gravity is not truly weak, but spread out, diluted across unseen dimensions or scales we cannot yet measure. Or perhaps its subtlety is not a flaw but a feature, finely tuned to make the universe stable enough for stars and life to exist. To reach those answers, we must look closer at the other forces that share the stage and see how their immense strength contrasts with gravity's whisper. When we compare the four fundamental forces side by side, we begin to see how extraordinary the difference truly is. The strong nuclear force, born from the exchange of gluons, binds quarks together to form protons and neutrons. It is the mightiest bond in the universe, holding the very heart of atoms intact. Without it, the nuclei of elements would disintegrate in an instant, and the periodic table would vanish like smoke. This force acts only over distances smaller than a trillionth of a meter, but within that tiny range, it reigns supreme. The electromagnetic force reaches far beyond the nucleus, shaping the chemistry of life and the glow of every star. It binds electrons to atoms, drives lightning through the sky, and carries information through the invisible waves of light. Like gravity, it has infinite range, but it can attract or repel, and in most places in the universe, positive and negative charges balance each other so perfectly that their effects cancel out. Then there is the weak nuclear force, the quiet transformer of the universe. It is the reason the sun shines at all, turning hydrogen into helium through a process called fusion. It allows neutrons to decay into protons, electrons, and neutrinos, subtly altering the building blocks of matter. Though its name suggests fragility, it is still immensely stronger than gravity. These forces are measured through what physicists call coupling constants numbers that tell how strongly particles interact through each force. The strong nuclear coupling is roughly 1, meaning the interaction is intense and immediate. Electromagnetism has a coupling of about 1/137, weaker but still significant. Gravity's effective coupling between two protons, however, is around 10 to the power of -39. To put it another way, the gravitational attraction between two protons is weaker than their electromagnetic repulsion by about 10 to the power of 36. It is difficult to visualize such an enormous gap. Imagine trying to weigh a single atom against the entire Earth. Even that comparison is not extreme enough. The numbers defy human comprehension, stretching beyond what language can comfortably hold. Yet the laws of nature are written in these ratios. Somewhere within them, lies the reason the universe has stars, planets, and people. If gravity were even a little stronger, stars would burn too hot and too quickly. The delicate balance of fusion in their cores would be destroyed, and the universe might be filled with short-lived giants rather than long-lived suns. Planets would orbit too close or be torn apart by tidal forces. The chemistry of life might never have time to emerge. If gravity were weaker, galaxies might never form at all, their matter drifting endlessly through the void. There is an exquisite precision in the way gravity is tuned, a harmony that allows both structure and survival. Some physicists wonder if this apparent fine-tuning hints at deeper laws we have yet to uncover. Others see it as evidence that countless universes may exist, each with different strengths of fundamental forces, and we simply happen to live in one where gravity's weakness allows complexity to arise. Either way, this quiet force, so feeble at the atomic scale, becomes the sculptor of the cosmos on the grandest scales imaginable. When you look at a galaxy, spinning like a great wheel of stars, gravity is what keeps it from flying apart. When you stand on the Earth, it is what binds the air to the sky and the oceans to the world. Even time itself flows differently under its influence, ticking slower near massive bodies and faster in the emptiness of space. Gravity does not shout like the strong force or spark like electromagnetism. It hums softly beneath all things, patient and enduring. This patience gives the universe its rhythm. Gravity lets matter gather, collapse, and ignite into stars. Those stars forge the elements of life in their cores and scatter them through supernova explosions. Over billions of years, those ashes form new systems, new planets, and new beginnings. Gravity is the quiet author of this cosmic cycle. It does not rush, it waits. So the paradox remains. The weakest force in the universe is also the one that gives the universe shape. Its faint whisper binds galaxies, holds moons in orbit, and makes the flow of time itself uneven. It works on scales so vast that we forget how small we are in its embrace. The magnet and the paperclip show us the contrast. The night sky shows us the truth. As we trace this force from the human scale to the cosmic scale, we begin to sense that its weakness may hide something profound. Maybe gravity's subtlety is not an accident, but a clue, a hint that our understanding of nature is still incomplete. To uncover its true nature, we must look deeper into its foundations, explore the hidden structure of space-time, and ask once more the question that has followed physics for centuries. What is gravity, really? To ask what gravity is, we must step back from the falling apple, from the orbiting planets, from the tides that rise and fall under the pull of the moon. We must strip away everything we see and ask what lies beneath the experience of weight itself. The feeling of gravity is familiar, yet it conceals something far deeper. When we stand on the surface of the Earth, we feel our feet pressed against the ground, but the ground is not pulling us down, it is pushing us up. The planet prevents us from continuing along the straight path through space-time that our bodies would naturally follow. Gravity, in the modern view, is not a tug at all. It is geometry. This revelation did not come easily. For centuries, Isaac Newton's picture of gravity ruled science. His law of universal gravitation was a triumph of human thought. He showed that every particle of matter in the universe attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. The equation could explain the motion of planets and comets, the fall of an apple, even the shape of the tides. It unified heaven and earth under a single law. But even Newton admitted he did not know what caused the attraction. He could describe how it worked, but not why. The idea of an invisible force acting instantaneously across the void troubled even him. For centuries, physicists were content to use his formula without asking deeper questions. It was not until the beginning of the 20th century that a new mind, shaped by both curiosity and rebellion, dared to challenge it. Albert Einstein looked at the universe differently. He imagined what it would feel like to fall freely, to be in an elevator descending through space, with no floor beneath his feet. In that moment, he realized something profound. The experience of free fall is indistinguishable from the absence of gravity. This insight became the seed of a revolution. He called it the equivalence principle, and from it grew the general theory of relativity. In this new picture, mass and energy tell space and time how to curve, and that curvature tells matter how to move. Gravity, therefore, is not a force transmitted across space. It is the shape of space itself. A planet orbits a star, not because it is pulled by an invisible thread, but because it is following the straightest possible path through curved space-time. The sun does not reach out to grasp the Earth. The sun bends the geometry of the universe around it, and the Earth simply moves along that geometry. Einstein's field equations captured this relationship in a set of mathematical symbols that changed physics forever. They showed that matter and energy could warp space-time, and that this warping could be dynamic, changing with time and motion. Out of those equations came predictions that seemed like fantasy at first: black holes where gravity becomes so strong that space folds in on itself, and gravitational waves that ripple across the universe like tremors in an invisible ocean. A century later, both predictions were confirmed. Astronomers found stars orbiting invisible points in space, moving so fast that only a black hole could explain their motion. Detectors on Earth recorded faint vibrations in space-time, the echoes of distant collisions between massive objects. Einstein's vision, once a thought experiment scribbled on paper, became measurable truth. Yet for all its success, general relativity remains incomplete. It describes gravity on large scales, planets, stars, galaxies, with exquisite accuracy. But when we try to apply it to the quantum world, to particles and forces that exist on scales smaller than atoms, it collapses. The mathematics breaks down. The smooth fabric of space-time that Einstein imagined cannot coexist with the jittery, probabilistic world of quantum mechanics. Somewhere between those two realms, our understanding fails. This failure is not small. It is fundamental. Quantum theory treats forces as interactions carried by particles. The electromagnetic force, for example, is mediated by photons. The strong nuclear force is carried by gluons. The weak nuclear force operates through W and Z bosons. Gravity, if it fits this pattern, should have a particle too, a graviton, but no one has ever detected it. Gravity is so weak that any individual graviton would be almost impossible to observe. Even if we built detectors the size of planets, the signal would be drowned by noise. Still, the idea of the graviton helps physicists imagine how gravity might work at quantum scales. In that picture, space-time is not a smooth continuum, but a foamy structure filled with virtual particles popping in and out of existence. Gravity would emerge from the exchange of gravitons, tiny quanta that transmit the curvature of space in discrete packets. But when scientists try to calculate how these gravitons interact, the equations explode into infinities. The theory refuses to behave. This is why quantum gravity remains one of the greatest unsolved problems in science. It is not just a missing piece. It is a missing foundation. Without it, we cannot fully understand the beginning of the universe, where both quantum effects and extreme gravity must have been at play. The singularity at the heart of a black hole and the instant of the Big Bang both lie beyond the reach of current theory. In those realms, space-time itself may dissolve into something deeper. And so we return to our question, what is gravity, really? Is it a curvature of geometry, a sea of virtual particles, or something we have yet to name? We know how it behaves. We can predict its effects with precision, but its true nature still hides behind the curtain of mathematical symbols. What we do know is this: gravity is not an external force acting upon space. It is space. It is the measure of how matter tells the universe to bend, how energy gives structure to emptiness, and how time itself slows in the presence of mass. To feel gravity is to feel the shape of space-time under your feet. To understand why gravity is so weak, we must now look at the others, at the strong, weak, and electromagnetic forces that dominate the quantum world, and see just how wide the gulf truly is. For only by comparing them can we hope to grasp the depth of gravity's mystery. When we try to compare gravity with the other three forces that rule the universe, we discover that each one speaks a different language. The strong nuclear force is the language of confinement, of quarks locked together so tightly they can never be isolated. The weak nuclear force is the language of transformation, of particles changing their identity through the invisible exchange of W and Z bosons. Electromagnetism is the language of light, the pulse that travels through every atom and across every star. But gravity is the language of the universe itself, written in the geometry of space and time. The strong force works only at distances smaller than a trillionth of a meter. Yet within that tiny realm, its grip is absolute. It is the reason the atomic nucleus exists at all. Without it, protons, each carrying a positive charge, would repel each other violently, but the strong force glues them together, its energy binding the core of every atom more tightly than any chemical bond ever could. To pull two quarks apart requires so much energy that new quarks appear instead, born from the vacuum itself. It is as if the universe refuses to let them be alone. The weak force, though less dramatic, plays a crucial role in shaping matter. It governs radioactive decay, the process by which one element becomes another. Deep within the sun, it allows protons to transform into neutrons, setting off the chain of fusion that produces the sunlight we see. The weak force operates through massive carriers, the W and Z bosons, which gives it a limited range. But without it, stars would not shine, and the elements of life would never form. Electromagnetism, meanwhile, extends endlessly. It binds electrons to nuclei and drives the chemistry of life. Every photon that leaves the sun, every lightning bolt that cuts the sky, every atom that holds its shape, all owe their existence to the electromagnetic field. Its beauty lies in its symmetry. The same equations that describe a spark in a wire also describe light, crossing the void between galaxies. Against this symphony of strength, gravity seems silent. The gravitational attraction between two protons is weaker than their electromagnetic repulsion by roughly 10 to the power of 36. That difference is so vast that, at the scale of atoms, gravity might as well not exist. Even the strong and weak forces outclass it by 30 or more orders of magnitude. Yet, on the scale of stars, planets, and galaxies, gravity dominates absolutely. This duality, insignificant in the small, supreme in the large, is one of the most astonishing facts of nature. The same force that holds your feet to the ground also shapes the orbits of galaxies, billions of light years away. It binds light itself, bending it around stars and black holes, sculpting the paths of photons into elegant curves. In the presence of mass, even time slows. A second on the surface of a planet passes differently from a second in deep space. Gravity does not just control motion, it defines reality. Still, physicists cannot shake the question of why it is so weak. If the universe is governed by four fundamental interactions, why does one of them lag so far behind the rest? Some have suggested that gravity's apparent weakness is an illusion, that its true strength might be hidden from us. Perhaps gravity spreads through dimensions beyond the three we can perceive. If so, what we feel is only a fraction of its total power, diluted across a higher dimensional space. Others look for answers in the constants of nature. The gravitational constant, the speed of light, and Planck's constant together define a natural scale known as the Planck scale, where gravity should become as strong as the other forces. But that scale is unimaginably far away at an energy of around 10 to the power of 19 giga-electronvolts, far beyond anything our most powerful accelerators could reach. Between the familiar world of atoms and the unreachable Planck realm lies a chasm of 32 orders of magnitude. That gulf is what scientists call the hierarchy problem. To bridge that gulf, we must find a framework that unites gravity with the quantum forces. But here, the challenge becomes overwhelming. General relativity describes a smooth, continuous space-time, while quantum mechanics describes a world of discrete probabilities. When we try to merge them, contradictions erupt. Quantum theory demands that fields fluctuate, but general relativity demands a fixed geometry for those fluctuations to occur. The two pictures refuse to fit, and yet, both must be true. We have seen the curvature of space-time in the bending of starlight and the orbit of planets. We have seen the quantum world in the behavior of electrons and photons. The universe cannot be two different realities at once. Somewhere, beneath both, there must be a deeper description that makes sense of all of it. Gravity stands as the great unifier and the great divider. It connects everything, yet resists being connected to anything else. It is the thread that ties the cosmos together, yet it slips through the fabric of quantum theory, like water through a net. That paradox drives the search for quantum gravity, the theory that could reconcile the infinite with the infinitesimal. Perhaps when we finally understand gravity's true nature, we will also understand why it is so weak. Maybe its faintness is a clue, not a defect. Maybe it whispers instead of shouts because it belongs to something far larger than the universe we can see. The journey to answer that question leads to one of the deepest frontiers of modern science, the quest to understand how the strengths of all forces compare, and why gravity seems so far removed from the others. For only by confronting those differences can we begin to glimpse what lies beyond. The gulf between gravity and the other forces is so immense that it almost feels deliberate, as though nature itself drew a curtain between the cosmic and the quantum. On one side lies the world of Einstein, where space-time bends under the weight of stars, and on the other lies the world of Planck and Heisenberg, where particles flicker in and out of existence, guided by probabilities instead of certainties. To unite these worlds is the great unfinished symphony of physics. In the quantum realm, the three non-gravitational forces, strong, weak, and electromagnetic, fit neatly within a framework known as the Standard Model. This model describes how particles interact through the exchange of force-carrying quanta. Gluons carry the strong force, photons carry electromagnetism, and the W and Z bosons carry the weak force. Each of these particles operates within the quantum field, a continuous sea of energy that fills all space. Even in perfect vacuum, these fields hum with activity, fluctuating with virtual particles that appear and vanish in less than a heartbeat. But gravity refuses to join this dance. The Standard Model treats forces as exchanges between particles in flat space-time, yet gravity is space-time. It cannot be inserted neatly as another participant in the quantum field because it defines the very arena in which those interactions take place. When physicists try to treat the gravitational field like any other quantum field, infinities arise, quantities that cannot be renormalized or tamed. The mathematics breaks, leaving us without a consistent theory. Despite this, we continue to probe the boundaries. The Planck length, about 1.6 times 10 to the power of negative 35 meters, is believed to be the smallest meaningful distance, where space-time itself becomes quantized. At scales smaller than that, the smooth geometry of Einstein's universe might dissolve into a foamy network of microscopic fluctuations. Some theorists imagine space-time as a kind of lattice, woven from fundamental loops or strings vibrating at the Planck scale. These ideas form the basis of approaches like loop quantum gravity and string theory, both attempts to describe gravity in quantum terms. Loop quantum gravity proposes that space is not continuous, but made of finite loops of energy. These loops connect in intricate patterns, forming a granular texture that gives rise to space-time itself. In this view, gravity emerges naturally from the geometry of those loops. String theory, by contrast, suggests that all particles, including gravitons, are tiny vibrating strings, each vibration corresponding to a different particle. The beauty of string theory is that it requires extra dimensions beyond the familiar three of space and one of time, offering a possible explanation for gravity's weakness. It might be leaking into those unseen dimensions. The idea of extra dimensions sounds like science fiction, yet it arises from serious mathematics. If gravity can extend into higher dimensional space, while the other forces remain confined to our familiar four-dimensional universe, then gravity's strength would appear diluted from our perspective. We would feel only a faint echo of its true intensity. Experiments have even tested this possibility, measuring gravity's behavior at extremely small distances to look for deviations from Newton's law. So far, none have been found, but the door remains open. Still, even these theories do not answer the most haunting question: why is gravity so perfectly tuned? The balance of its weakness allows stars to burn for billions of years, planets to form stable orbits, and atoms to exist without being crushed. It may be that if gravity were stronger, the universe would have burned itself out in a flash of violent creation. If weaker, matter might never have condensed into anything more than a diffuse mist. Somewhere between these extremes lies the narrow range that makes life possible. This precision has led some physicists to invoke the anthropic principle, the idea that the laws of physics appear fine-tuned for life, because only in such a universe could observers like us exist to notice. Others resist this explanation, seeking instead a deeper law that fixes the strength of gravity in a natural way. But until that law is discovered, we must acknowledge the uncanny coincidence that allows the cosmos to exist in its present form. When we gaze into the night sky, we are seeing gravity at work on the grandest scale. Every star, every galaxy, every cluster of galaxies is shaped by its pull. It sculpts the large-scale structure of the universe, weaving filaments of matter that stretch across billions of light years. Yet, in the same universe, gravity is powerless to bind two atoms together. It is as if nature uses gravity as the tool for architecture, but not for detail. Perhaps this is the key to understanding it. Gravity may not need to be strong to be essential. It governs the stage, not the actors. It sets the curvature in which all events unfold. The electromagnetic, weak, and strong forces build the structures of matter, but gravity determines the stage upon which those structures move, evolve, and eventually fade. Without it, there would be no stage, no motion, no cosmic story at all. As we close our look at what gravity truly is, we are left with both wonder and incompleteness. We can describe how it curves space-time, how it shapes orbits, how it slows time itself. But we cannot yet say what it is made of, where it comes from, or why it is so gentle. To answer that, we must compare it more precisely to its counterparts, to measure their strengths and see what secrets those ratios hold. For within those differences, the gap between the fury of the strong force and the whisper of gravity may lie the explanation of the universe's hidden design. And so, we turn now to the next step in our journey, where we weigh the strengths of the forces themselves and seek the first hints of why gravity stands apart. The story of the universe is written in the language of its forces. Every motion, every spark, every structure that has ever existed depends on the balance between four interactions that govern all things. They are the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. Together they weave the fabric of reality, yet their strengths differ so wildly that it seems impossible they could belong to the same universe. To understand why gravity is so weak, we must first see how powerful the others truly are. Imagine a single atom of hydrogen, the simplest element in existence. It is made of just one proton and one electron, bound together by the electromagnetic force. The electron orbits the proton not because of gravity, but because opposite electric charges attract. If we were to calculate the gravitational attraction between the same two particles, it would be weaker than their electric attraction by roughly 10 to the power of 40. That is a 1 followed by 40 zeros. The difference is so extreme that if gravity were the only force in the atom, the electron would never bind to the proton at all. The universe would be a cloud of scattered particles, forever drifting in emptiness. This disparity is not limited to atoms. It pervades every corner of existence. The strong nuclear force, which binds protons and neutrons together inside atomic nuclei, is about 10 to the power of 38 times stronger than gravity. The weak nuclear force, which controls radioactive decay and powers the fusion inside stars, is around 10 to the power of 32 times stronger. Even electromagnetism, which operates across infinite distances like gravity, overwhelms it by a factor of 10 to the power of 36. These are not small differences, they are cosmic gulfs. To visualize such magnitudes, imagine standing beside a mountain and comparing it to a grain of sand. Then imagine comparing that grain of sand to a single atom, and the atom to a subatomic particle. Gravity is that subatomic whisper next to the mountain roar of the other forces, and yet, it is the one that shapes the cosmos itself. Physicists often express the strength of a force using something called a coupling constant, which describes how strongly particles interact. The strong nuclear force has a coupling constant of roughly 1, meaning its effects are immediate and intense. The electromagnetic force has a coupling constant of about 1 divided by 137. It is weaker, but still potent across distance. The weak force's constant is smaller still, because its carriers are heavy particles that cannot travel far. Gravity's effective coupling, by contrast, is almost unimaginably tiny, around 10 to the power of negative 39 between two protons. Despite being so feeble, gravity has a property that none of the others share. It always attracts. There is no negative mass, no opposite version that cancels it out. Every piece of matter adds to the gravitational pull of the whole universe. While positive and negative electric charges balance out and nuclear forces fade beyond the atomic nucleus, gravity accumulates. Its reach may be weak, but it never stops. That is why it governs the architecture of galaxies and the evolution of stars. It wins not by strength, but by persistence. Still, the sheer scale of the difference is unsettling. The same laws of nature produce a force that can crush matter into a black hole and another that cannot lift a paperclip. Why should the universe allow such imbalance? Why should one force dominate the small and another rule the large? These are not idle curiosities. They are clues to something deeper. The disparity in force strength becomes even more puzzling when we consider how they behave as energy increases. Quantum theory tells us that the effective strength of the forces changes with scale, a phenomenon known as running coupling. As particles collide at higher energies, the strong force weakens, the electromagnetic and weak forces grow stronger, and all three seem to approach similar values at extremely high energy levels, around 10 to the power of 16 giga-electron-volts. This convergence suggests that they may once have been unified, different expressions of a single primordial force in the early universe. But gravity does not join this convergence. Its strength remains vastly lower, even at those enormous energies. Only at the unreachable Planck scale, around 10 to the power of 19 giga-electron-volts, does gravity finally become comparable. That separation of 3 orders of magnitude in the exponent, roughly 10 to the power of 3, corresponds to a difference in energy of 1,000 trillion times. It is this enormous gap that defines the hierarchy problem. Why is the Planck scale so much higher than the energy scales of the other forces? Why did nature separate gravity from the rest by such an enormous gulf? If all forces were truly unified at the beginning of time, why does gravity appear so diluted now? These questions lie at the heart of theoretical physics, and they have driven generations of scientists to search for patterns hidden in the numbers. In the early universe, when everything was compressed into an unimaginably hot and dense state, the strengths of all forces may have been closer together. As the cosmos expanded and cooled, symmetry broke, and the forces split apart, each taking on its own identity. It is possible that gravity's weakness emerged from that symmetry breaking, not as an accident, but as a consequence of deeper mathematical laws we have yet to uncover. The idea that the forces were once one echoes through every modern theory that seeks unification. It inspired grand unified theories, or GUTs, which attempt to merge the strong weak and electromagnetic forces into a single mathematical framework. These models predict that at high enough energies, protons could decay, transforming one form of matter into another. Experiments have searched for such decay for decades, but none have yet observed it. If gravity were included in that picture, we might finally have a theory of everything, a single principle explaining all interactions from quarks to galaxies. But gravity remains elusive, hovering just beyond reach. The contrast between the strength of the forces and their roles in the universe is poetic. The strong force binds matter together. The weak force changes it. Electromagnetism gives it structure and light. And gravity shapes the stage upon which it all unfolds. Each plays its part in the cosmic drama, and together they create the balance that allows the universe to exist as it does. But what if gravity is not truly weak? What if we are seeing only a fraction of its full effect, the rest hidden beyond our senses? Perhaps gravity spreads across dimensions we cannot perceive, or perhaps its energy is bound up in the very fabric of space-time itself, leaking away into regions we can never reach. These possibilities lead to theories of extra dimensions and brain worlds, ideas that stretch the imagination, but may hold the key to solving the hierarchy problem. To explore them, we must first look more closely at that problem itself, the vast difference between the gravitational and electroweak scales, and the question of why the universe allows such separation. For in that mystery lies the doorway to the next chapter of our understanding of the cosmos. When we examine the numbers that define the universe, we find that the strengths of the forces are not random. They are set by constants that seem exquisitely precise, as if balanced on a razor's edge. A small change in any of them would reshape reality itself. The fine structure constant, which determines the strength of electromagnetism, is roughly 1 divided by 137. If it were slightly larger, atoms would collapse. If smaller, they would never form stable structures. The coupling constants of the strong and weak forces are equally vital, setting the rules for nuclear stability and the birth of elements inside stars. Yet gravity's constant, the one that defines its strength, stands apart. It is so tiny that even when multiplied by the mass of the sun, it yields only a whisper compared to the forces that operate within a single atom. Physicists often measure these constants using natural units, built from the three most fundamental quantities in physics: the speed of light, Planck's constant, and Newton's gravitational constant. From them arises the Planck mass, about 2 × 10 to the power of -8 kilograms, or roughly the weight of a dust grain. It may seem small, but in particle physics terms it is enormous, about 10 to the power of 19 giga-electronvolts, the energy scale at which gravity would become as strong as the other forces. The particles we study in laboratories, such as electrons or quarks, have masses that are smaller by factors of 10 to the power of 17 or more. That staggering difference defines the hierarchy problem. Why does the Planck scale sit so far above the electroweak scale, the level where the weak and electromagnetic forces merge? Why should nature separate these energies by such a colossal gulf? It is as if 2 clocks in the same universe tick at utterly different speeds, one counting the tremors of atoms, the other measuring the curvature of the cosmos. The equations of physics give no clear reason for this separation. They simply accept it as fact. Some scientists argue that gravity might not truly be weak at all. What if its strength appears small, only because it is spread across more dimensions than we can see? Imagine the universe as a thin film floating in a higher dimensional space. All the particles and forces we know, electrons, photons, quarks, gluons, are confined to that film, called a brane. But gravity, tied to the geometry of space-time itself, might leak beyond the brane into the larger space, called the bulk. To us, it would appear faint, because we feel only the portion that remains on our brain. This concept forms the foundation of certain theories inspired by string theory, such as the Randall-Sundrum model. In that framework, the universe could contain extra dimensions curled up so tightly that we cannot perceive them. Gravity, unlike the other forces, could extend into those hidden directions. The apparent weakness of gravity would then be a kind of illusion, a side effect of geometry rather than an intrinsic property. Experimentalists have searched for signs of these extra dimensions by testing gravity at extremely small distances, looking for deviations from Newton's inverse square law. If gravity begins to leak into additional dimensions, its strength should increase slightly, at scales smaller than a millimeter. So far, the tests have found no such deviation, but they continue to push the limits, probing ever smaller ranges with exquisite precision. Each null result tightens the boundaries of what is possible, guiding theorists toward more refined ideas. Even without extra dimensions, the hierarchy problem remains a deep puzzle. Some physicists have proposed that hidden symmetries in nature might protect the weak scale from drifting upward to the Planck scale. Supersymmetry, for instance, predicts that every known particle has a heavier partner with opposite spin properties. These superpartners could cancel the quantum fluctuations that would otherwise make the Higgs boson the particle responsible for giving mass to others absurdly heavy. If supersymmetry exists, it would help explain why the weak force operates far below the energy scale of gravity. But despite decades of searching, no superpartners have yet been found. Experiments at the Large Hadron Collider have pushed the limits higher and higher, but the expected signatures remain absent. Still, the idea persists because it elegantly ties together many loose threads. If supersymmetry or a related mechanism exists, it may not only solve the hierarchy problem, but also provide a bridge toward quantum gravity. Meanwhile, another perspective arises from the study of cosmic inflation, the rapid expansion that occurred in the earliest moments of the universe. During that era, gravity and quantum fields interacted in ways that blurred their distinction. Tiny fluctuations in space-time grew into the seeds of galaxies. The energy scales involved were close to the Planck energy, suggesting that gravity may have played a much stronger role in shaping the early universe than it does today. Perhaps its apparent weakness is not a constant at all, but a relic of cosmic evolution, a result of how energy and geometry settled as the universe cooled. When we step back, we see that gravity's faintness may be both an obstacle and a gift. It keeps the universe stable, allowing complex structures to emerge over billions of years. If gravity were stronger, stars would collapse too quickly, and life might never arise. If weaker, matter might never clump into galaxies. The fine balance we observe seems almost miraculous, yet it could be the inevitable outcome of deeper laws we have yet to uncover. We can measure, compare, and calculate the strengths of the forces, but we still do not know why they differ so much. That question is what drives the search for a deeper unification. Perhaps the weakness of gravity is not a flaw but a signpost, pointing toward the underlying architecture of reality. To follow it, we must step beyond the visible universe and into the strange realm of theoretical possibility, where extra dimensions, brains, and higher energies may hold the answers we seek. To understand how such extraordinary ideas emerged, we must explore the hierarchy problem itself, the mathematical riddle that forced physicists to ask why gravity stands alone among the forces of nature, and how that separation might one day be bridged. The deeper we follow this thread, the clearer it becomes that gravity's weakness is not a trivial curiosity, but a fundamental clue about the structure of the universe. The hierarchy problem is the key that exposes it. On paper, it begins as a question about scales, but in truth, it is a question about meaning. Why should nature choose to separate gravity from the other forces by such an enormous gulf of energy? Why should the Planck scale, where gravity becomes strong, stand so far above the electroweak scale, where the weak and electromagnetic forces merge? In physics, this separation looks like a kind of fine-tuning. The Higgs field, which gives mass to particles, operates at energies around 100 giga-electron volts. Yet the quantum corrections to the Higgs mass, predicted by quantum field theory, naturally tend to push it upward toward the Planck scale of 10 to the power of 19 gigaelectronvolts. To keep it low, the corrections must cancel with extraordinary precision to something like 1 part in 10 to the power of 17. That level of balance is so delicate that it feels unnatural, as if the universe were balancing on a knife's edge for no reason. Physicists dislike coincidences. When the numbers line up so perfectly, they suspect a hidden principle at work. Supersymmetry once promised to explain that balance by pairing every known particle with a heavier counterpart that cancels out those quantum corrections. But as experiments continue to rule out the predicted mass ranges, the idea faces increasing tension. Without such symmetry, the hierarchy problem returns in full force. Why is the weak scale so small compared to the gravitational scale? Why does gravity not rise to meet it? Some theories suggest that gravity's true strength might indeed match the other forces at the Planck scale, but we perceive it as weak because most of its influence is spread out, not confined to our visible dimensions. Imagine the universe as a vast stage with hidden wings extending into directions we cannot see. The strong, weak, and electromagnetic forces perform only on the main stage, while gravity moves freely through all the hidden spaces. Its apparent faintness is merely the result of its energy being distributed across a larger arena. This vision was crystallized in the late 20th century through the concept of brane worlds. In those models, our universe is a 4-dimensional surface, 3 of space, and 1 of time floating inside a higher dimensional bulk. All familiar matter and forces are confined to the brain, like actors bound to a screen, but gravity seeps through the bulk, touching both our world and others that might exist alongside it. From our perspective, this leakage makes gravity seem weak, but from the viewpoint of the higher dimensions, it may be as strong as the other interactions. One of the most striking examples of this idea came from the Randall-Sundrum model, which proposed that gravity could be localized in a 5-dimensional space, its strength varying exponentially across the extra dimension. This geometric warping could naturally explain why gravity appears so weak on our brain, without requiring any fine-tuning of constants. The mathematics suggested that the very shape of the extra dimension could suppress gravity's strength, producing the enormous hierarchy between the Planck and electroweak scales. Though elegant, these ideas remain speculative. Experiments have searched for evidence of extra dimensions by studying high-energy particle collisions and measuring gravity at microscopic scales. If gravity truly leaks into additional dimensions, its behavior should deviate slightly from Newton's law at small distances, growing stronger than expected. Sensitive instruments have probed down to fractions of a millimeter, but no deviation has yet been found. The absence of evidence does not rule out the theory. It simply pushes the possible size of those extra dimensions ever smaller. Even without new dimensions, the notion that gravity's weakness might arise from geometry remains compelling. In Einstein's general relativity, the curvature of space-time already determines how gravity behaves. It may be that the same curvature, extended into hidden dimensions, shapes the apparent strength we measure. In that sense, the hierarchy problem could be not a coincidence, but a consequence of the universe's architecture. The quest to solve it has led physicists to some of the most imaginative ideas ever proposed. From supersymmetry to string theory, from brane worlds to holographic principles, each new attempt aims to bring gravity and quantum mechanics together under one roof. The hope is that somewhere among these ideas lies a pattern, a clue, or a symmetry that will finally reveal why gravity stands apart. Yet even as we search, gravity continues to play its quiet, patient role. Its weakness makes the cosmos vast and long-lived. Stars burn slowly, galaxies form gently, and time itself unfolds at a pace that allows life to emerge and wonder at its own existence. It may be that the very problem we struggle to solve is also the reason we are here to ask it. For now, we live in a universe of asymmetry, a cosmos where 3 forces rule the small and 1 rules the vast. But perhaps this imbalance is temporary, a sign that we are missing the deeper connection that ties them all together. The hierarchy problem is not merely a mathematical puzzle. It is an invitation to look beyond the boundaries of what we can see, into the hidden dimensions where the true nature of gravity might be waiting. And so we reach the edge of what our current theories can explain. To move forward, we must venture into the realm of higher dimensions, where gravity may no longer be confined to the familiar fabric of space and time. There, in the folds of geometry itself, might lie the answer to why the weakest force rules the grandest stage. The deeper we look into the laws of nature, the more they resemble a code written with exquisite precision. Every number, every constant, every ratio seems to exist in perfect balance. Yet among these symmetries lies a riddle so immense that it divides the universe into two realms, the realm of the quantum and the realm of the cosmic. That riddle is the hierarchy problem, the question of why gravity is so astonishingly weaker than the other forces of nature. To glimpse the scale of the mystery, imagine shrinking yourself down to the size of an atom. Inside the nucleus, the strong nuclear force dominates, binding quarks together into protons and neutrons, and those protons and neutrons into the nucleus itself. Its power is overwhelming, but it fades beyond the edge of the atom. Surrounding it is the electromagnetic force, pulling electrons into orbit and giving rise to chemistry, light, and life. Beyond that, the weak force quietly governs decay and transformation, turning neutrons into protons and releasing energy within the hearts of stars. Gravity, in this microscopic world, is nearly non-existent. Its pull between two protons is so faint that it is roughly 10 to the power of 36 times weaker than their electric repulsion. Now expand your view outward, beyond the atom, beyond the Earth, beyond the solar system. The farther you go, the stronger gravity appears to become. It binds planets to stars, stars to galaxies, and galaxies to the great cosmic web. It sculpts the universe into filaments of light and darkness that stretch across billions of light years. Gravity, once invisible in the world of the very small, becomes the single dominant force in the world of the very large. This reversal is one of nature's most beautiful ironies. The weakest of all forces becomes the ruler of the cosmos. Physicists have spent decades trying to explain why this is so. The central question is this: why is gravity 10 to the power of 32 times weaker than the electroweak force? Why does the scale of gravity, known as the Planck scale, sit so far above the scale of the other interactions? This gulf is so vast that it defies intuition. The Planck scale, the energy where gravity becomes comparable in strength to the other forces, lies at about 10 to the power of 19 giga-electron volts, while the electroweak scale, where the weak and electromagnetic forces unify, lies near 100 giga-electron volts. Between these two lies a desert, an enormous void in energy, where no known force bridges the gap. At first glance, this may sound like a technical issue, a question of measurement, but it is far more profound. It challenges the idea that the universe's laws are unified and natural. In physics, a theory is considered natural when its parameters arise from fundamental principles rather than coincidence. The hierarchy problem tells us that something, somewhere, is missing. The numbers do not simply fail to match, they defy the idea of unity itself. The problem becomes especially clear when we look at the Higgs field, the invisible field that gives mass to particles. The Higgs boson, discovered in 2012 at the Large Hadron Collider, is the quantum ripple of this field. Its mass, about 125 giga-electron volts, sits squarely in the electroweak range. But according to quantum field theory, that mass should be vastly higher. Every particle that interacts with the Higgs contributes a quantum correction to its mass, and these corrections grow with energy. When we calculate them up to the Planck scale, the result becomes enormous, so large that it should push the Higgs mass to nearly the Planck energy itself. For it to remain low, those corrections must cancel almost perfectly, to 1 part in 10 to the power of 17. Such precise cancellation feels unnatural. It suggests that either there is an unknown symmetry keeping the Higgs mass small, or our understanding of the connection between gravity and the quantum world is incomplete. Supersymmetry, one of the most elegant ideas in modern physics, offers one potential explanation. It proposes that for every known particle, there exists a heavier partner particle whose quantum effects cancel the enormous corrections. The delicate balance that keeps the Higgs light would then emerge naturally, not through coincidence, but through symmetry. But supersymmetry has not yet shown itself in experiments. Decades of searching at the world's most powerful colliders have failed to find the predicted superpartners. They may be heavier than we expected, or the theory may need revision. Some physicists hold out hope that the symmetry exists, but is broken in subtle ways. Others suspect the truth may lie elsewhere, in dimensions we cannot see. The hierarchy problem has also led to the exploration of the idea that gravity's weakness might be an illusion caused by geometry. In a universe with extra spatial dimensions, gravity could spread out across them, diluting its apparent strength. We feel only the faint echo that remains in our four-dimensional world. This notion, though strange, fits neatly within certain versions of string theory, which require additional dimensions for mathematical consistency. In this picture, our universe is a three-dimensional surface, a brane floating in a higher dimensional space called the bulk. While the electromagnetic, weak, and strong forces are confined to the brane, gravity seeps into the bulk, leaking into those hidden dimensions. The more it spreads, the weaker it appears to us. From the viewpoint of the higher dimensional universe, gravity might not be weak at all. Its strength could rival that of the other forces, hidden by the vastness of the space it occupies. To test this idea, scientists have searched for deviations from Newton's law of gravity at very small distances. If gravity truly extends into extra dimensions, its strength should begin to increase slightly at submillimeter scales. Experiments using exquisitely sensitive torsion balances have pushed these tests to the limits of precision, but so far, Newton's law holds true down to the smallest measurable distances. Even so, the possibility of extra dimensions remains alive. The absence of deviation merely constrains their size, suggesting that if they exist, they must be smaller than a fraction of a millimeter. Whether through hidden symmetries, extra dimensions, or some deeper mechanism still unknown, the hierarchy problem stands as one of the great signposts of modern physics. It tells us that the separation between gravity and the other forces is not random. It is the result of something profound, something that connects the geometry of space-time to the structure of quantum fields. The answer may one day reveal why the universe looks the way it does, why matter clumps into stars, why time flows as it does, and why we are here to ask these questions at all. To move closer to that answer, we must look beyond the surface of our familiar dimensions and into the strange possibility that gravity's weakness is not a flaw, but a clue that it may, in fact, be escaping into a higher reality that surrounds our own. At the heart of the hierarchy problem lies the gulf between two numbers that define the universe's structure. One is the electroweak scale, around 100 giga-electron-volts, where the weak and electromagnetic forces unify. The other is the Planck scale, around 10 to the power of 19 giga-electron-volts, where gravity becomes as strong as the other interactions. Between them yawns a gap so vast that it seems absurd to belong in a single theory of nature. Imagine a bridge stretching across an ocean, 1 trillion times wider than the galaxy, and you begin to sense the magnitude of this separation. This chasm defines the question that has haunted physics for half a century. Why does nature permit such a split between the scales that define its forces? If the fundamental laws of the cosmos emerged from a single origin, why did gravity choose such a different stage? The Planck scale arises naturally from three constants that sit at the foundation of all physical law: Newton's gravitational constant, the speed of light, and Planck's constant. When combined, They yield a natural measure of mass, energy, and length quantities that set the boundaries of space-time itself. The Planck length, about 1.6 times 10 to the power of negative 35 meters, represents the smallest meaningful distance, beyond which our concepts of space and time cease to apply. The Planck energy, roughly 10 to the power of 19 giga-electronvolts, marks the point at which gravity's strength can no longer be ignored in quantum interactions. The electroweak scale, by contrast, arises from the dynamics of the Higgs field and the masses of the W and Z bosons. It defines the realm where the weak nuclear force and electromagnetism merge into a single interaction. In our world, that energy scale sets the mass of the fundamental particles that make up ordinary matter. If the Higgs field's energy were much higher, the masses of quarks and leptons would be enormous, and atoms could not exist in their present form. The hierarchy problem, therefore, is not just about numbers. It is about existence. The smallness of the electroweak scale compared to the Planck scale determines everything from the stability of atoms to the length of a human life. The Higgs boson's mass, roughly 125 giga-electronvolts, is stable only because something somewhere prevents it from being dragged up to the Planck energy by quantum corrections. That something remains one of the deepest mysteries in physics. Supersymmetry, as imagined by theorists in the late 20th century, was meant to provide an elegant answer. In a supersymmetric universe, every known particle has a superpartner with opposite spin characteristics. Fermions, which make up matter, would have bosonic partners that carry forces, and bosons, which mediate forces, would have fermionic partners. These pairs would perfectly balance each other's quantum contributions to the Higgs mass, preventing the catastrophic increase predicted by the Standard Model alone. It was a beautiful idea. Supersymmetry offered not only a natural solution to the hierarchy problem, but also a path toward unification. It predicted that at sufficiently high energies, all forces might merge, and that the lightest of the superpartners could even account for dark matter. For decades, physicists built experiments to find evidence of these superparticles. Yet, as each collider reached higher energies and found nothing, hope began to fade. Still, the absence of proof does not mean the theory is wrong. The superpartners could exist at energies just beyond our current reach. The Large Hadron Collider, for all its power, probes only a minuscule fraction of the Planck scale. Perhaps nature hides its symmetries at energies too high for us to access. Or perhaps it reveals them in subtler ways, through the fine structure of particle interactions or the behavior of the vacuum itself. Another path to understanding the hierarchy problem came from the idea that gravity might not be weak by nature, but weakened by geometry. Imagine our universe as a sheet stretched through a higher dimensional space. The familiar forces electromagnetism, the weak force, and the strong force are confined to that sheet, unable to move through the extra dimensions. Gravity, however, as a property of space-time, can spread into them. Its field lines, instead of being concentrated in our 3 dimensions, extend into a wider arena, diluting the force we observe. This concept was developed into precise models known as large extra-dimension theories. In these frameworks, the true fundamental scale of gravity could be as low as the electroweak scale, around 1 trillion electronvolts. The apparent weakness of gravity would then be an illusion caused by its energy leaking into additional dimensions that we cannot perceive. To visualize this, imagine light spreading from a lamp. In 2 dimensions, the light fills a circle, and its brightness diminishes as the circle expands. In 3 dimensions, it spreads as a sphere, and its brightness fades even faster. If there were more dimensions for light to occupy, its intensity in our familiar space would appear weaker still. Gravity might behave in exactly this way, spreading through extra dimensions and appearing faint only because we see a small slice of its true power. This idea inspired an entire generation of experiments. Physicists designed tabletop setups capable of measuring gravitational attraction at distances smaller than 1 millimeter, where any deviation from Newton's inverse square law might hint at hidden dimensions. At the same time, high-energy particle colliders searched for telltale signs of gravitons escaping into those dimensions, tiny losses of energy that might betray the existence of a broader cosmos. So far, every test has confirmed the familiar picture. Gravity still follows Newton's law down to distances of about 50 micrometers, and no missing energy signals have appeared at colliders. Yet, the limits themselves are meaningful. They constrain how large the extra dimensions could be, and they show that if the hierarchy problem has its origin there, it must hide on scales smaller than we can currently explore. Even without proof, the concept of hidden dimensions remains one of the most compelling ideas in theoretical physics. It connects Einstein's curved spacetime with quantum field theory, offering a geometric explanation for the vast difference between gravity and the other forces. It also provides a natural stage for string theory, which requires additional dimensions for its equations to remain consistent. In such a framework, gravity is not an isolated anomaly, but a window into the structure of higher dimensional space. The hierarchy problem may therefore be more than a puzzle. It may be a signpost, pointing us toward a deeper level of reality. The weakness of gravity, the lightness of the Higgs, and the vastness of the Planck scale might all emerge from the same hidden architecture. If so, the true unity of nature lies not in the forces themselves, but in the geometry that shapes them. To follow that trail, we must now step into the realm of higher dimensions, where the familiar boundaries of space and time give way to something stranger, a universe that may be far larger and more complex than anything we can see. When physicists first proposed that gravity might leak into extra dimensions, the idea seemed almost reckless. For centuries, space was assumed to have 3 dimensions: height, width, and depth, woven together with time to form the 4-dimensional fabric Einstein described. But as the mathematics of quantum gravity evolved, it began to suggest that reality could be far richer than appearances allowed. The equations of string theory, developed in the late 20th century, revealed that the universe might contain not 4 but 10, or even 11 dimensions. The 3 we move through daily are merely a fraction of the whole. In string theory, the smallest building blocks of the universe are not point-like particles but one-dimensional strings that vibrate in different ways. Each vibration corresponds to a distinct particle. One pattern produces an electron, another produces a quark, and another produces a graviton, the hypothetical quantum of gravity. The beauty of this idea is that the graviton arises naturally from the mathematics. It is not an afterthought or an added hypothesis. It is built into the structure of the theory itself. But strings can only behave consistently in higher dimensions. When physicists tried to make the theory work in the familiar 4 dimensions, contradictions arose. Only by adding extra spatial dimensions did the equations remain stable. Most of those dimensions, according to the theory, are compactified, curled up so tightly that they are invisible to us. They might be folded into intricate shapes called Calabi-Yau manifolds, smaller than the nucleus of an atom. Within those folds could lie the hidden symmetries that determine the properties of all matter and forces. In this higher dimensional view, our entire universe might be like a membrane, a brain, floating within a vast, multi-dimensional space known as the bulk. Everything we know, from atoms to galaxies, exists on this brain, while gravity alone can extend into the bulk. The more dimensions it explores, the weaker it appears within our slice of reality. The concept is astonishing, yet the mathematics supports it, and its implications reach far beyond the hierarchy problem. If gravity is free to move through extra dimensions, it could connect distant regions of the bulk in ways that seem impossible within 4-dimensional spacetime. The gravitational field might loop back upon itself, linking separate branes or creating shortcuts known as wormholes. These higher dimensional connections could help explain phenomena that remain mysterious, such as the nature of dark matter or the behavior of black holes. In some scenarios, entire parallel universes might exist just beyond our reach, separated from us, not by distance, but by direction, in a higher dimensional space. The Randall-Sundrum model refined this vision by suggesting that the extra dimension need not be large, but could be warped, its geometry stretching or compressing space, so that gravity's strength changes exponentially across it. In such a warped geometry, the hierarchy between the weak and gravitational forces could arise naturally from the shape of space-time itself. The smallness of gravity would then be not a coincidence, but a direct consequence of curvature. The universe, in this view, hides its deepest laws in its very geometry. To test these ideas, scientists turned again to experiment. If extra dimensions exist, they might reveal themselves in subtle ways, perhaps through the production of microscopic black holes in high-energy collisions, or through slight changes in how gravity behaves at tiny distances. Some versions of string theory even predict that certain particles could move between branes, momentarily vanishing from our universe before reappearing elsewhere. The Large Hadron Collider has searched for such anomalies, scanning for missing energy that could signal gravitons escaping into the bulk. So far, the results have been silent, but silence in science often means only that the story is not yet finished. Even without direct evidence, these theories carry deep philosophical weight. They suggest that what we call weakness may be a kind of perspective illusion. Gravity could be as fundamental and powerful as any other force, but its energy is spread across dimensions our senses cannot perceive. We live in a shadow of a larger reality, measuring only a faint echo of a deeper truth. The hierarchy problem, in this light, transforms from a question about scales into a question about perception. What we call weak may simply be wide, its influence dispersed through the hidden structure of space. The mathematics of string theory and brain-world cosmology provides a consistent, though incomplete, framework for this possibility. But it also opens a new frontier of questions. How do we detect a dimension we cannot see? What would happen if two branes collided? Could gravity's escape into higher dimensions explain the missing mass of the cosmos, the dark matter that outweighs all visible stars combined? Some physicists believe the answer might indeed connect to dark matter and dark energy, those unseen forces that dominate the universe. If gravity interacts with hidden dimensions, its effects could appear to us as invisible mass or accelerated expansion. The weakness of gravity would then be the same mystery that drives cosmic acceleration, a single phenomenon seen from two sides. Whether these ideas prove true or not, they change how we think about reality. They remind us that weakness and strength are not absolute, but relative to the framework in which we measure them. Gravity's faint pull on the paperclip may be the gentle shadow of a far more intense interaction, echoing through unseen dimensions. The hierarchy problem is not yet solved, but it has become the compass guiding modern theoretical physics. It tells us that the path to unification, the dream of a single theory explaining all forces, runs through the geometry of space-time itself. To follow it, we must leave behind our familiar three-dimensional intuition and venture into the higher dimensional landscape that might hold the key to everything. From here, the next step in the story leads directly into those hidden dimensions and the search for proof that gravity truly escapes beyond our visible universe. It is a journey that begins with mathematics but may one day reshape how we see existence itself. Imagine standing at the edge of the universe, looking out into a darkness that stretches beyond imagination. You might think there is nothing beyond it, that space ends where your vision fails. But what if that darkness hides something far more vast than distance, something that moves not outward, but sideways, into dimensions you cannot see? The idea that our universe may not be the whole of existence is not new. Ancient philosophers once spoke of hidden worlds layered upon one another, invisible realms woven through the same space we inhabit. But in the language of modern physics, this old dream has found mathematical form. The proposal is bold. The three dimensions of space and the one dimension of time we experience every day may be part of a larger framework, one that includes additional dimensions beyond our perception. These extra dimensions were first suggested not by mystics, but by physicists seeking unity. In the early 20th century, Theodore Kaluza and Oscar Klein noticed that when they extended Einstein's equations of general relativity to 5 dimensions, the mathematics naturally produced both gravity and electromagnetism from a single geometric framework. Their insight was revolutionary. It hinted that the forces of nature might not be distinct entities at all, but different aspects of a deeper geometry. The universe, in this view, could be a grand architectural structure whose hidden corridors contain the laws we struggle to understand. But there was a problem. If an extra dimension existed, why could we not see it? Klein proposed that the 5th dimension might be compactified, curled up so tightly that it was smaller than any measurable scale, like a line that looks one-dimensional from a distance but reveals a circular thickness up close. This hidden dimension could be wrapped around itself at scales smaller than a trillionth of a meter. For decades, the idea remained a mathematical curiosity, overshadowed by the success of quantum theory and the standard model of particle physics. But as physicists sought to unify all forces, Kaluza and Klein's vision returned in a new guise: string theory. In this modern framework, particles are not points but vibrating strings, and those vibrations require extra dimensions for the theory to remain consistent. 10 dimensions for superstring theory, 11 for its more general extension, known as M-theory. The extra dimensions in string theory are not vast empty directions. They are compactified in complex shapes called Calabi-Yau manifolds. These geometric forms twist and fold in ways that determine the physical constants of our universe. The strengths of forces, the masses of particles, even the properties of light, may all depend on the shape of these invisible dimensions. In essence, the universe we experience is a shadow cast by the hidden geometry beneath it. If this sounds abstract, consider what it implies for gravity. In string theory, the graviton, the hypothetical particle that carries the gravitational force, can move freely through all dimensions, not just the 3 we know. The other forces, bound to the strings that vibrate within our familiar space-time, are confined to our 4-dimensional world. Gravity alone roams beyond it. That freedom could explain why gravity seems so weak. Its energy is not lost, only spread thin across dimensions we cannot reach. This idea gained momentum at the turn of the 21st century, when physicists Lisa Randall and Raymond Sundrum proposed that the universe could exist as a brane, a 3-dimensional surface, floating in a 5-dimensional space. In their model, the 5th dimension is not flat but warped, its geometry curved in such a way that gravity appears exponentially weaker in our region of space. To observers confined to our brain, this warping would make gravity seem faint, even though its true strength remains comparable to the other forces in the higher dimensional bulk. The beauty of the Randall-Sundrum model lies in its simplicity. It does not require enormous extra dimensions, only a subtle curvature in the hidden 5th. That curvature acts like a lens, focusing the intensity of gravity away from our world. The weakness we perceive is therefore not a flaw in nature's design, but a perspective effect, a trick of geometry. Testing such ideas requires exquisite precision. Physicists have built experiments that measure the attraction between small masses at millimeter and submillimeter scales, searching for even the tiniest deviation from Newton's law of gravitation. If extra dimensions exist, their influence should appear as a slight increase in gravity's strength at small distances. So far, the results have shown no deviation, but each experiment tightens the limits, shrinking the possible size of those hidden dimensions. Even in failure, the search teaches us something profound. It shows how delicately balanced our universe is. If extra dimensions exist, they must be small enough, or warped enough, to leave the familiar world almost untouched. Yet their presence could still explain the hierarchy problem, the vast difference between the electroweak and Planck scales, by revealing that the true gravitational strength is not small, but hidden. This perspective transforms gravity's weakness into a doorway. Instead of seeing it as a gap in our understanding, we can see it as a clue to the deeper structure of reality. The faintness of gravity could be the echo of unseen dimensions, whispering to us from beyond the reach of sight. And if that is true, then the fabric of space-time is not a flat sheet, but a vast, multi-dimensional landscape, folded and curved in ways that shape everything we experience. To move deeper into this mystery, we must explore how such higher dimensions could exist without betraying themselves to observation. We must imagine a universe where the familiar three dimensions of space are just a surface within a greater whole, a place where gravity escapes into the unseen, carrying with it the secrets of the cosmos. If our universe is truly just a brain suspended in a higher dimensional expanse, then everything we call reality, the galaxies, the atoms, the light from the sun, is confined to a surface, thinner than a shadow. Only gravity can step beyond that surface, wandering into the vast hidden bulk. In such a universe, the weakness of gravity is not a flaw to be fixed, but a sign of its freedom. It does not live solely in our world. It belongs to a wider stage. To grasp this, imagine a two-dimensional world drawn on the surface of a balloon. The creatures that live on that surface know only length and width. They can move forward and backward, left and right, but they have no awareness of up or down. Their universe is complete. Yet to us, who can see in 3 dimensions, it is only the skin of a larger object. If we press a finger against the balloon, the creatures feel the distortion, but cannot see what causes it. To them, the finger's presence is a mysterious force. In the same way, our 3-dimensional space may be curved or disturbed by things moving in higher dimensions that we can sense only through the faint tug of gravity. In the brain world picture, all the familiar forces of nature, the strong, weak, and electromagnetic, are tied to the brain like threads woven into fabric. Their particles, bound by the mathematics of quantum fields, cannot escape into the bulk. Gravity, however, is different because it is not a force within space, but a property of space itself. The curvature that defines gravity naturally extends into every available dimension. Like a sound that echoes through empty halls, it spreads across the bulk, losing intensity as it moves farther from our world. That spreading, that dilution of its power, is what makes it seem weak. The equations of the Randall-Sundrum model describe this dilution beautifully. They show that the geometry of the 5th dimension acts as a kind of gravitational filter. On our brain, the field lines of gravity are bent and stretched by the curvature of space, making the force fall off more rapidly than Newton's simple inverse square law would suggest. Yet from the viewpoint of the higher dimensional bulk, gravity is not weak at all, it is perfectly ordinary. Its apparent faintness is an illusion created by the warping of space. This warping has measurable consequences. If it exists, it should slightly alter the way gravity behaves at small scales. To test this, experimental physicists have built sensitive devices that measure gravitational attraction between tiny masses, separated by distances smaller than a millimeter. These experiments must eliminate every source of vibration, temperature drift, and electromagnetic interference, for the signals they seek are weaker than the faintest breath. Over the past 2 decades, such measurements have probed gravity down to about 50 micrometers, and yet no deviation has appeared. The results confirm that, at least down to those distances, Newton's law still holds. But the absence of evidence is not the same as evidence of absence. The extra dimension could be smaller than the scales we can currently probe, curled into a shape too tight to detect. Or the warping could be so strong that its effects on local gravity are hidden beneath measurement noise. The search continues, because the stakes are enormous. A single verified deviation would transform our understanding of space, time, and the origins of the universe. Beyond the laboratory, the concept of extra dimensions has found unexpected connections to other mysteries. In the realm of black holes, for example, the idea that gravity can move through additional dimensions helps explain certain paradoxes. When a black hole forms on our brain, it might extend as a long filament, a black string, into the bulk. Its true shape, invisible to us, could stretch across dimensions we cannot perceive. Such a structure might even allow information to escape in ways that challenge our conventional notions of event horizons. At the cosmic scale, extra dimensions could influence how the universe expands. Some models suggest that the accelerated expansion we attribute to dark energy might instead result from gravitational effects leaking into the bulk. If gravity weakens across the vastness of space because part of its pull escapes into higher dimensions, galaxies would appear to drift apart faster than expected. What we call dark energy could then be not a mysterious substance, but a geometric consequence of hidden dimensions, shaping cosmic evolution. Even the question of the universe's birth takes on new meaning in this framework. In certain brain cosmologies, our Big Bang was not the beginning of all existence, but the result of a collision between brains within the bulk. Two higher dimensional worlds, moving through space, could have brushed together for an instant, releasing energy that became our universe. The aftershocks of that collision might still echo today in the form of cosmic background radiation or subtle gravitational waves. These possibilities are breathtaking, yet they remain grounded in mathematics and in the relentless pursuit of consistency. The goal of physics is not to multiply fantasies, but to find the simplest description that explains all observable facts. Extra dimensions may sound extravagant, but they offer an elegant way to unify gravity with the quantum world. They allow us to imagine that all forces are geometric in origin, each arising from the shape of space-time itself. If this is true, then gravity's weakness is not an accident of scale, but a window into a deeper reality. It is the one force that reminds us the universe might be larger than we can ever see, that space itself has more directions than we can travel. We live on a thin membrane of existence, surrounded by dimensions that remain forever hidden, yet constantly shaping everything we know. To understand this hidden structure fully, we must turn to the mathematics of compactification, the process that folds higher dimensions into shapes small enough to evade detection. In those geometric folds may lie the reason the forces have their specific strengths and why gravity, though weak in our world, may be infinitely powerful in the space beyond. If the extra dimensions of space truly exist, they must be hidden so completely that we never sense their presence in everyday life. The air we breathe, the light we see, and the atoms that make up our bodies all move within the familiar three dimensions of length, width, and height. Yet according to string theory and its higher dimensional offspring, M theory, there may be 6 or 7 more spatial dimensions compactified into spaces smaller than a proton. These hidden dimensions are not empty voids, but intricate geometric forms, curled upon themselves like knots in space-time, shaping the constants that define our universe. To understand this idea, imagine an ant walking along the surface of a thin wire. From far away, the wire appears one-dimensional, a simple line. But the ant, being tiny, can also move around the wire's circumference. What seemed one-dimensional to us is, to the ant, two-dimensional, a long direction and a curled one. Now shrink that curled direction until it becomes smaller than any conceivable scale, smaller than the Planck length itself, and you have a glimpse of what physicists mean by compact dimensions. They exist, but they are so tightly folded that only the tiniest vibrations of fundamental strings can feel them. In the mathematics of string theory, the shapes of these extra dimensions are not arbitrary. They must satisfy complex equations of balance and curvature. The most famous of these shapes are Calabi-Yau manifolds, multidimensional surfaces that are simultaneously curved and symmetrical. Each possible Calabi-Yau shape corresponds to a different set of physical laws. The geometry determines how strings vibrate, and those vibrations define what particles and forces can exist. Change the geometry, and you change the universe. This idea implies something extraordinary. The constants of nature might not be universal at all, but geometric. The strength of gravity, the masses of particles, even the number of families of quarks and leptons, could all depend on the hidden topology of space. The weakness of gravity in our world could thus be the consequence of the way those extra dimensions are folded. In a different geometric configuration, gravity might be much stronger, or the universe might never form stable matter at all. Some physicists believe that these compactified dimensions could even provide an explanation for the so-called landscape of string theory, the vast number of possible vacuum states that the equations allow. Each state corresponds to a different shape of the extra dimensions, each with its own physical constants. If this landscape is real, then our universe may be only one of countless others, each with different laws, floating like bubbles in an ocean of higher dimensional space. In that vast ensemble, gravity's weakness may be not a mystery, but a selection effect. We exist in the version of reality where gravity is weak, because only here can galaxies, stars, and life itself emerge. But theories are only as good as their predictions, and physicists have worked tirelessly to find ways to detect the presence of these hidden dimensions. One of the most direct approaches comes from searching for small deviations in Newton's inverse square law. If gravity spreads through extra dimensions, its strength would not fall off exactly as the square of distance. Instead, it would drop off more quickly at large scales, but grow slightly stronger at very small scales. Sensitive torsion balance experiments have tested this behavior down to 50 micrometers, confirming that no deviation has yet appeared. However, this still leaves enormous room at smaller distances where the effects could hide. Another route of investigation comes from high-energy collisions. If gravity can move through extra dimensions, then when particles collide at enormous energies, such as in the Large Hadron Collider, tiny amounts of gravitational energy could leak into the bulk. This leakage would appear as missing energy in the detectors, an invisible recoil that might hint at gravitons escaping our brain. The collider has searched for such signals in billions of collisions, and though none have been found, the absence itself refines our understanding, setting upper limits on the size and curvature of the hidden dimensions. Even more ambitious are the searches using cosmic observations. If extra dimensions influence gravity on the largest scales, they could alter the motion of galaxies or the expansion rate of the universe. Some cosmological models suggest that what we perceive as dark energy might be the geometric effect of gravity leaking into higher dimensions, reducing its pull within our brain and allowing space to expand more rapidly. Measurements of the cosmic microwave background and the distribution of galaxies are now precise enough to test some of these models. And though the evidence remains inconclusive, the door remains open. The notion that gravity might travel beyond our universe also leads to startling possibilities about communication between brains. In certain models, multiple brains could exist parallel to our own, each hosting its own version of physics. Gravitational waves, ripples in space-time itself could, in theory, cross from one brain to another, faintly influencing the structure of our cosmos. Some physicists have speculated that unexplained signals in gravitational wave data might one day reveal such interactions, though for now they remain far beyond detection. If these ideas sound strange, they are meant to. The mathematics of higher dimensions forces us to abandon our ordinary intuitions. We live in a universe where the vastness of space hides in the smallest folds of geometry. What we call empty space may, in fact, be alive with unseen curvature, each twist and loop shaping the destiny of matter and the flow of time. And yet, for all its mystery, this vision gives us something profound, a way to see gravity's weakness, not as a problem, but as a key. The faintness of its pull may be the signature of the higher dimensional architecture that underlies reality. In that sense, gravity's escape into extra dimensions could be the very mechanism that allows the universe to exist in its delicate balance, strong enough to form galaxies, weak enough to let stars live for billions of years. Perhaps the most beautiful consequence of this idea is philosophical. If gravity truly reaches into other dimensions, then our universe is not an isolated island, but part of a greater whole. What we call the universe might be only a fragment of a larger, multi-dimensional structure, connected by the threads of gravity that weave through all. We may never see those hidden realms directly, but their influence touches us every moment in the pull that binds the Earth to the Sun and the stars to the galaxies beyond. In the end, the search for extra dimensions is a search for understanding, an attempt to read the deeper blueprint of existence. Gravity's weakness, the oldest puzzle in physics, may be the universe's quiet way of telling us that there is more to reality than meets the eye. To move forward, we must now confront the last and most stubborn barrier: gravity's incompatibility with the quantum world. If extra dimensions offer a geometric explanation for its weakness, quantum gravity may offer the key to its nature. To grasp both, we must step into the frontier where space-time itself becomes quantized, where the smooth curves of Einstein's geometry dissolve into a lattice of energy and probability. The search for the origin of gravity's weakness leads inevitably to the deepest question of all: what is gravity when seen through the lens of quantum mechanics? The force that sculpts galaxies and bends light should, by every principle of physics, also emerge from the same quantum foundations that govern all other forces. Yet every attempt to merge these two realms, Einstein's smooth spacetime and the jittering, probabilistic world of the quantum, has broken down. Gravity is the one piece of the cosmic puzzle that refuses to fit. In the quantum picture, every force is mediated by particles. The electromagnetic force is carried by photons, massless quanta that dance through space at the speed of light. The strong nuclear force binds quarks together through gluons, and the weak force operates through heavy W and Z bosons. Each force is a conversation among particles, exchanged through these carriers. Gravity, by extension, should also have a quantum messenger, the graviton, a massless particle of spin, too, that mediates the curvature of spacetime. But the mathematics of such a particle is treacherous. When physicists attempt to quantize Einstein's equations to treat the gravitational field as a quantum field like any other, they encounter infinities that refuse to cancel out. In quantum electrodynamics, or the strong force, these infinities can be renormalized, meaning the theory can be adjusted so that its predictions remain finite. Gravity resists such adjustment. The infinities grow without limit, implying that our theory loses meaning at extremely high energies. This is why gravity remains separate from the quantum world. To understand where it might break down, we must turn to the Planck scale, once more the domain where spacetime itself ceases to be smooth. At lengths shorter than the Planck length, around 1.6 times 10 to the power of negative 35 meters, the very fabric of the universe becomes turbulent, a sea of microscopic fluctuations known as quantum foam. The geometry of spacetime writhes and bubbles, creating and annihilating miniature black holes in a storm of energy. In this realm, the idea of a continuous spacetime surface fails. Instead, space and time themselves must be quantized, built from discrete units, as atoms build matter. One approach to describing this quantum geometry is called loop quantum gravity. In this theory, spacetime is not a continuous fabric, but a network of loops, woven together into a vast cosmic lattice. Each loop represents a quantum of space, and together they define the structure of the universe at the smallest scales. Gravity emerges naturally from the way these loops twist and connect. The curvature of spacetime is replaced by the spin and linkage of these loops, and the strength of gravity arises from their configuration. Loop quantum gravity has one great virtue. It does not require extra dimensions or unseen entities. It works directly from the principles of general relativity and quantum mechanics, merging them into a single framework. In this vision, the weakness of gravity might simply reflect the rarity of quantum interactions among these loops. The gravitational field is a manifestation of geometry itself, not a separate force to be compared with electromagnetism or the nuclear interactions. Yet loop quantum gravity, for all its elegance, faces challenges. It describes the structure of spacetime beautifully, but struggles to connect with the world of particles. It explains geometry, but not the forces that operate within it. String theory, on the other hand, unites both particles and geometry within one framework, though at the cost of great mathematical complexity. In string theory, gravity is not an add-on, but a necessity. The graviton appears automatically as one of the vibrational modes of a string. The theory's consistency requires it. This has made string theory the leading candidate for a theory of quantum gravity. But it also introduces a vast landscape of possible solutions, each corresponding to a different way the extra dimensions might be shaped. Among these countless possibilities, our universe is only one. To bridge these two worlds, the loops of geometry and the vibrations of strings, physicists have turned to another concept: the holographic principle. It suggests that all the information contained within a region of space can be described by a theory defined on its boundary. In other words, the three-dimensional universe we experience could be the projection of information encoded on a distant, two-dimensional surface. This idea, once born from black hole physics, has found mathematical form in what is known as ADS-CFT correspondence, a duality between a gravitational theory in a curved space and a quantum field theory on its boundary. If this principle is correct, gravity and quantum mechanics are not enemies at all. They are two sides of the same coin, reflections of one another across the boundary of space-time. The weakness of gravity might then arise because we live inside a holographic projection where the gravitational effects are diluted through the encoding of information. Quantum gravity, in all its forms, points toward the same truth. Gravity is not just another force. It is the shape and texture of reality itself. Its apparent weakness is the price of universality. Unlike the other forces, which act only between specific kinds of particles, gravity acts on everything that possesses energy. Its reach must be infinite. Its influence subtle. It cannot be confined or screened. That universality, paradoxically, makes it seem weak. And yet, when enough matter gathers, gravity's hidden strength reveals itself. It can crush atoms, bend light, and trap time within a black hole. On the cosmic scale, it dominates everything. Its whisper becomes a roar. That duality, the faintness in the small and the omnipotence in the large, may be the signature of its quantum nature. The search for quantum gravity is not just a technical challenge. It is a quest to understand the architecture of existence. Whether the answer lies in loops, strings, or holograms, it will reshape not only physics, but philosophy. It will tell us whether space-time is fundamental or emergent, whether the universe is continuous or pixelated, whether reality itself is built from information. The weakness of gravity, seen through this lens, becomes not a failure of symmetry, but a clue to the unity of all things. It whispers that beneath the particles and forces lies something deeper, a single fabric that connects energy, matter, and geometry into one. At the frontier where quantum mechanics and gravity collide, black holes stand as the great teachers. These cosmic abysses are not only the densest objects in existence, but also the purest laboratories for studying the marriage of quantum theory and space-time. Inside their gravity, time slows to nothing, and space folds upon itself. To understand how gravity works at the quantum level, we must understand black holes, because they reveal the contradictions most clearly. Einstein's theory predicts that once matter collapses beyond a certain point, nothing, not even light, can escape. The boundary of that region is called the event horizon. To a distant observer, the horizon marks the end of all information, a one-way surface where the universe's knowledge disappears. But in the quantum world, nothing can vanish completely. Every process must be reversible. Information, even if transformed, must never be lost. This is where the trouble begins. In the 1970s, Stephen Hawking discovered that black holes are not entirely black. Quantum effects near the event horizon cause them to emit radiation, now called Hawking radiation, arising from virtual particle pairs that appear and separate at the edge of the hole. One particle falls in while the other escapes, carrying away a tiny bit of the black hole's energy. Over unimaginable timescales, This radiation causes the black hole to evaporate. Yet Hawking's calculations suggested that the radiation carried no information about what had fallen in. If true, the information about the collapsed matter would be lost forever, a direct violation of quantum theory. This paradox sparked decades of debate and led to one of the most profound ideas in physics, the holographic principle. The insight came from studying how information might be stored on the surface of a black hole. When Jacob Bekenstein calculated its entropy, the measure of the information hidden within, he found that it was proportional not to the black hole's volume, but to its surface area. This result hinted that the information contained within any region of space could be represented on its boundary. From this seed grew a revolutionary thought. Perhaps the entire universe works like this. Perhaps all the information describing the contents of space is encoded on a lower dimensional surface surrounding it. Our three-dimensional experience might be a projection of quantum data written on the edges of space-time itself. In this view, gravity emerges from the interactions of those boundary degrees of freedom, much as temperature emerges from the random motion of atoms. This holographic vision gained mathematical power through a framework called ADS-CFT correspondence. In this duality, a gravitational theory in a curved five-dimensional space-time anti-de Sitter space is exactly equivalent to a quantum field theory without gravity on its four-dimensional boundary. What happens in the bulk of space can be described entirely by equations on its edge. The geometry of the bulk encodes the quantum dynamics of the boundary, and vice versa. Gravity and quantum mechanics, once enemies, are shown to be mirrors of the same underlying reality. If the universe obeys such a holographic principle, then gravity's weakness may arise because it is not fundamental. It could be an emergent phenomenon, like the surface tension of water, real, measurable, and powerful, yet arising from the collective behavior of countless smaller interactions. The curvature of space-time would then be the large-scale manifestation of microscopic quantum entanglement, linking every region of the cosmos. Entanglement is the invisible thread of the quantum world, binding particles across distance in a web of correlations. In recent years, physicists have discovered that the structure of space-time itself might depend on these entanglements. In certain models, when quantum entanglement decreases, space begins to tear. When it increases, space grows connected. From this perspective, gravity could simply be the tendency of the universe to maximize entanglement. The smoothness of space-time would be the visible form of invisible quantum relationships. This idea transforms gravity's weakness into something elegant. If the gravitational field emerges from quantum entanglement, its apparent faintness reflects the stability of that underlying network. The stronger the coherence of the quantum web, the gentler the curvature it produces. The entire universe might be a single vast quantum system, and gravity the faint echo of its entangled structure. Black holes again provide the testing ground. In the holographic view, the surface of a black hole encodes every piece of information that falls within it, preserving quantum consistency. As the black hole evaporates, that information is released slowly through correlations in the Hawking radiation, maintaining the fundamental rule that nothing is truly lost. The paradox dissolves. Gravity and quantum mechanics coexist after all, each expressed through the geometry of the other. When seen through this lens, gravity's role in the cosmos changes. It is no longer just a force pulling matter together. It becomes the fabric that holds reality itself coherent. Its weakness allows the universe to remain stable. Its slow hand-shaping galaxies without tearing apart the quantum underpinnings beneath. Its universality, the fact that it acts on everything with energy, reflects the fact that everything participates in the same web of quantum information. As these ideas evolve, they reveal an astonishing unity. The strong and weak nuclear forces, electromagnetism, and gravity may all be different manifestations of a single fundamental process. The geometry of quantum information, the forces that hold matter together, and the curvature that guides planets through space could arise from the same deep principle, encoded in the entanglement patterns of the cosmos. The search for a complete theory of quantum gravity continues, not only in equations but also in experiment. Observations of black hole mergers by gravitational wave detectors, the images of event horizons captured by radio telescopes, and the subtle polarization of the cosmic microwave background may one day reveal traces of spacetime's quantum grain. Each clue brings us closer to understanding how gravity and the quantum realm intertwine, and why their relationship gives rise to the universe we inhabit. To move forward, we must explore how this hidden unity may connect with the mysteries that still surround the cosmos: dark matter, dark energy, and the unseen majority of existence that reveals itself only through gravity's pull. These invisible components may not be separate substances at all, but manifestations of gravity's true, multidimensional nature. At the edge of understanding, gravity and quantum mechanics seem to whisper the same secret from different directions. One speaks in the language of geometry, the other in the language of probability. One curves the paths of stars, the other determines the behavior of particles. Yet when we listen closely enough, their voices begin to merge. The closer we approach the Planck scale, the point where energy, space, and time intertwine, the more it appears that they are not separate truths, but different expressions of one reality. The holographic principle and the concept of emergent spacetime suggest that gravity might not be a fundamental force at all, but the byproduct of deeper quantum processes. If true, this could explain not only its weakness, but also its universality. Every form of energy participates in gravity because every form of energy contributes to the underlying quantum entanglement from which spacetime itself arises. The curvature we perceive as gravitational attraction could simply be the large-scale reflection of those entanglement patterns rearranging themselves to maintain balance. To see how this might work, imagine the universe as a vast network of quantum information, a cosmic web where each point of space corresponds to a node in a vast entangled structure. When energy or mass appears, it disturbs that web. The network shifts its connections, and those changes in connectivity manifest to us as curvature in space-time. Matter tells space how to curve, and space tells matter how to move, because both are part of the same informational system. Gravity's weakness, then, is a sign of how robust the network is. The web of entanglement resists distortion. Only enormous masses, stars, galaxies, and black holes can bend it enough to create visible effects. This vision has begun to take mathematical form in recent years through studies of quantum entanglement, entropy, and tensor network models. In these frameworks, the geometry of space emerges naturally from the way information is shared among quantum states. When entanglement decreases between regions, the corresponding parts of spacetime drift apart. When it increases, they draw closer together. From the equations that describe these relationships, gravity appears automatically as an emergent phenomenon, much like temperature arises from the collective motion of molecules. Such a picture reshapes how we think about the cosmos. It means that gravity is not a thing acting upon other things. It is the collective behavior of the universe itself. It is the geometry of existence adjusting to maintain equilibrium. And because it is an emergent property, not a direct interaction, its strength is not determined by fundamental charges, but by the density and coherence of the underlying quantum information. In a sense, gravity is the gentlest whisper of reality's deepest order. This way of seeing gravity also casts new light on dark matter and dark energy, those two invisible phenomena that dominate the universe. We know dark matter by its gravitational pull. It shapes galaxies and bends light, but we do not know what it is made of. Dark energy, even more mysterious, drives the acceleration of cosmic expansion. Both appear only through gravity's behavior. If gravity is emergent, then these cosmic mysteries might not be substances at all, but signs that our current equations describe only part of the deeper quantum geometry. Some researchers have proposed that the effects attributed to dark matter could arise naturally if space-time has a kind of elasticity. In an emergent gravity model, the apparent extra mass needed to explain galactic rotation might be an illusion created by how quantum information reorganizes itself across large scales. Similarly, dark energy might represent the inherent pressure of the quantum vacuum, the residual tension in space-time's entanglement network as it evolves. In this view, gravity's weakness and the dominance of dark energy are two sides of the same coin. Both reflect the immense stability and subtle flexibility of the underlying structure. Black holes again act as the crucibles of these ideas. They are the places where the quantum and gravitational worlds meet most violently. If the holographic principle is correct, then the surface of a black hole encodes all the information of its interior, and as it radiates away energy, that information must gradually emerge. Some modern calculations suggest that correlations in the Hawking radiation do indeed carry this hidden data, preserving the unbroken logic of quantum mechanics. If this is true, then gravity's geometry may be nothing more or less than a manifestation of information flow the way the universe keeps its accounts balanced. The faintness of gravity could thus be a reflection of how information is distributed. Every particle in the universe contributes to the entanglement structure, but because that web is so vast and coherent, no single disturbance can shift it much. Only the combined mass of planets or stars produces a noticeable curvature. This may also explain why gravity cannot be screened or blocked. Information itself cannot be isolated from the system that defines it. Everything participates in the same network, so everything feels gravity's influence, however small. At the cosmic scale, this subtle force becomes destiny. It is gravity that turns chaos into structure, pulling matter from uniformity into galaxies, stars, and worlds. It is gravity that shapes time, creating the slow unfolding of cosmic history. Its weakness is its strength. It acts gently enough to allow complexity to form, patiently enough to let life emerge. If it were stronger, the universe would have collapsed into black holes long ago. If weaker, it would have drifted apart before the first stars could ignite. Quantum gravity, therefore, does more than unify physics, it explains existence itself. The faintness of the gravitational field ensures the stability of atoms, the longevity of stars, and the quiet unfolding of cosmic evolution. The smallness of Newton's constant may be the single number that makes meaning possible. It is as though the universe tuned itself so that gravity, born from the quantum structure of reality, would guide creation without consuming it. As physicists push further into this frontier, they dream of a final synthesis, a single theory that will reveal how space-time, matter, and energy emerge from the same quantum code. Whether that code is written in strings, loops, or holographic entanglements, it will tell the story of how the weakest of all forces became the architect of everything. The search continues, but even now, one truth stands clear. Gravity's weakness is not a defect. It is the signature of unity. It is the quiet breath of a universe built from the intertwining of the vast and the small, where every star and every particle are bound together by the same invisible thread. From here, the journey carries us into the shadows of the cosmos itself, to the unseen majority of matter and energy that gravity alone can reveal. For in understanding how gravity behaves with the invisible, we may finally glimpse its true strength. When we look into the night sky, we see only a fraction of what exists. The stars, planets, and glowing gas clouds that fill our telescopes make up less than 5% of the universe. The rest is invisible, 95% hidden from all direct observation. Yet its presence is undeniable, revealed through the quiet pull of gravity and the accelerating expansion of space itself. This unseen cosmos is divided into two mysteries: dark matter, which binds galaxies together, and dark energy, which drives them apart. The discovery began with an inconsistency. In the 1930s, Astronomer Fritz Zwicky studied clusters of galaxies and found that they moved as if held by a gravitational force far greater than visible matter could provide. Later, in the 1970s, Vera Rubin measured the rotation of galaxies and saw the same pattern. Stars at the edges moved too fast, refusing to slow, as Newton's laws would predict. Something unseen was adding gravity, something that neither emitted nor absorbed light. It was called dark matter. Today, we know dark matter outweighs all visible matter by more than 5 to 1. It does not interact with electromagnetic radiation, so it cannot be seen, but it shapes the universe on every scale. It forms vast halos around galaxies, scaffolds for cosmic structure, and the invisible skeleton of the web that connects clusters across space. Gravity is the messenger of its existence, the only bridge between what we can see and what we cannot. But gravity also reveals something even stranger. In the late 1990s, measurements of distant supernovae showed that the universe's expansion is accelerating. Instead of slowing under its own gravity, space itself is stretching faster and faster. The only explanation consistent with Einstein's equations is that some form of energy inherent to the vacuum is pushing everything apart. This phenomenon was named dark energy, and it now accounts for nearly 70% of the total energy in the cosmos. The two great unknowns, dark matter and dark energy, show that gravity interacts with what we cannot see. They are not merely add-ons to our model of the universe. They define it. Without dark matter, galaxies would fly apart. Without dark energy, the universe would collapse or remain static. Together, they determine the fate of everything. Some theories propose that dark matter consists of undiscovered particles, weakly interacting massive particles or axions that barely touch ordinary matter, except through gravity. Others suggest that dark matter may not be particles at all, but a manifestation of gravity behaving differently on large scales, perhaps influenced by extra dimensions or emergent quantum geometry. In that view, what we call dark matter could be the echo of space-time's hidden structure, the residue of gravity's deeper nature leaking into the visible world. Dark energy is even more enigmatic. It may be the energy of the quantum vacuum itself, arising from fluctuations that fill empty space. Or it could be a sign that our understanding of gravity breaks down on cosmic scales. If gravity emerges from quantum entanglement, as some modern theories propose, then the accelerated expansion of space might reflect the way information spreads across the universe, gravity's large-scale counterpart to the microscopic processes that give rise to space-time itself. Either way, gravity remains the link between the seen and the unseen. It reveals the invisible by the way it bends light and shapes time. Through its weakness, it allows us to detect the faintest hints of what lies beyond perception. Every galaxy's motion, every subtle lensing of distant starlight, every ripple in space-time carries the imprint of this hidden universe. Perhaps the most profound realization is that gravity's weakness makes this possible. If gravity were stronger, dark matter and dark energy would be overwhelmed by violent collapse or expansion. Instead, gravity's gentle pull balances the cosmic equation, allowing the visible and invisible to coexist in harmony. The faintest of all forces turns out to be the most revealing. It shows us that reality is far larger than we imagined, that most of the universe hides, not in darkness, but in mystery. And as we peer deeper into that mystery, we come to see that gravity is not just the force that holds worlds together, it is the translator between what exists and what can be known. It connects the luminous and the invisible, the material and the geometric, the measurable and the infinite. In understanding it, we are not merely learning about the universe, we are glimpsing the structure of reality itself. For all its frailty in the laboratory, gravity becomes almighty on the grandest scales. The same force that cannot lift a paperclip against a small magnet is the sculptor of stars, the architect of galaxies, and the engine that drives the evolution of the cosmos. Its quiet persistence, acting over billions of years, turns chaos into order. It weaves the universe into the vast structure we observe today. In the beginning, the universe was nearly uniform, an expanding sea of light and hydrogen gas. Tiny fluctuations in density, born from quantum ripples in the first instant of cosmic inflation, provided the seeds of structure. Gravity amplified them. Regions slightly denser than average began to pull in more matter, their gravity growing stronger as they accumulated mass. Over time, those small irregularities grew into clouds, clouds into stars, and stars into galaxies. This slow accumulation reveals gravity's true character. It is not a sudden or violent force. It is patient, cumulative, and inevitable. Its weakness allows it to act as a sculptor rather than a destroyer. If gravity were as strong as the electromagnetic or nuclear forces, the universe would have collapsed into clumps of matter almost immediately after the Big Bang. There would be no stars, no planets, no chemistry, no time for life to arise. Its gentleness is the reason the cosmos can evolve. Inside collapsing clouds of gas, gravity compresses matter until the temperature and pressure rise high enough to ignite nuclear fusion. In that moment, gravity and the nuclear forces strike a delicate balance. The inward pull of gravity is matched by the outward pressure of fusion. This equilibrium creates the long, stable lives of stars. For billions of years, they burn quietly, transmuting hydrogen into helium and heavier elements. Without gravity's weakness, that balance would fail. Stars would burn too fast or collapse too soon. When the nuclear fuel runs out, gravity reclaims what it once held in check. Massive stars implode under their own weight, releasing titanic energy as supernovae. These explosions scatter heavy elements, carbon, oxygen, iron across space, enriching the universe with the ingredients for planets and life. Every atom in the human body was forged in such a star, shaped by the patient hand of gravity. On still larger scales, gravity gathers billions of stars into galaxies. Within each galaxy, it orchestrates the cosmic dance of rotation, creating spiral arms and elliptical structures. Between galaxies, it builds immense filaments that stretch across the universe, forming a cosmic web hundreds of millions of light-years wide. Even the empty voids between these structures exist because gravity drew matter away from them. The universe's pattern, its vast beauty exists because gravity's pull is both universal and restrained. And then, at the extreme, gravity reveals its power without limit. In the hearts of galaxies, it collapses matter into black holes, compressing mass into singular points, where density and curvature become infinite. Time slows, light bends, and the laws of physics themselves falter. From the event horizon outward, gravity dictates everything. Yet even in this ferocity, its weakness at small scales allows such entities to exist without devouring the cosmos wholesale. The balance between strength and subtlety is the hallmark of gravity's mastery. It also shapes time itself. According to Einstein's general relativity, gravity is not a force in the usual sense. It is the curvature of space-time caused by energy and mass. When you stand on Earth, you feel weight, not because a force pulls you downward, but because space-time is curved toward the planet's center, guiding your path along that curve. Near massive objects, time slows relative to regions farther away. In this way, gravity determines the rhythm of the universe, orchestrating the flow of moments as surely as it guides the motion of stars. Gravity's influence extends even to the fabric of the cosmos as a whole. The expansion of the universe, once thought to be uniform, is now understood to be shaped by the interplay between gravity and dark energy. In the early universe, gravity slowed the expansion, allowing galaxies to form. Later, dark energy began to dominate, accelerating the expansion again. This delicate, cosmic tug-of-war defines the past and future of everything. From atoms to galaxies, from the heartbeat of stars to the birth of time itself, gravity connects all scales. It is the universal translator between the very small and the very large. Its weakness is not a limitation but a design, a fine-tuning that makes the universe possible. Were it slightly stronger, stars would burn out before planets could cool. Were it weaker, matter would never have condensed into anything solid. The cosmos, as we know it, exists in the narrow window between these two extremes, a window opened by gravity's restraint. In this sense, gravity's true strength lies not in its force, but in its harmony. It allows complexity to emerge. It governs the shape of time, the birth of light, and the destiny of matter. It is the bridge between quantum chaos and cosmic order. Its weakness, seen from another angle, is the greatest act of precision in nature, the fine balance that lets existence unfold rather than collapse. Perhaps this is the lesson hidden in the stars. What appears weak in isolation becomes unstoppable in unity. The same law that cannot lift a paperclip holds entire galaxies together. The same gentle curvature that barely tugs on an atom binds the universe across billions of light years. Gravity's strength is not measured in magnitude, but in permanence. It never stops acting, never ceases to connect. And when we look at the night sky, filled with light from stars long dead and galaxies billions of years old, we are seeing gravity's masterpiece, the structure of existence itself, carved slowly from the silence of space. It is the one force that defines both the beginning and the end, the shaper of matter and the guardian of time. When physicists measure the universe, they find a pattern that seems impossibly delicate. Every constant, every interaction, every ratio among the forces appears to fall within a narrow band that allows existence to unfold. Gravity's weakness, so perplexing on its own, is one of the most precise balances in nature. If it were stronger by even a fraction, the universe would have collapsed long before life could arise. If weaker, the matter that makes stars and planets would never have gathered at all. The cosmos seems tuned for complexity, as though the numbers themselves were chosen with intent. This realization is known as fine-tuning. It does not imply design in a mystical sense, but rather a profound sensitivity in the laws of physics. The gravitational constant, the strength of electromagnetism, the ratio of the proton to electron mass, and the density of dark energy all fall within a narrow range that permits long-lived stars, stable atoms, and chemical diversity. Shift any of them slightly, and reality as we know it unravels. The universe appears balanced on a knife's edge. Some see this as coincidence, a fortunate outcome of random cosmic evolution. Others suspect a deeper principle at work, something that binds these numbers together in ways we do not yet understand. The dream of unification, the theory of everything, aims to reveal that what we call fine-tuning is not tuning at all, but the natural outcome of a deeper symmetry. Yet until that theory is found, the universe's precision remains a riddle that inspires both awe and unease. The anthropic principle offers one possible explanation. It states that the universe must have properties compatible with the existence of observers, because otherwise there would be no one to notice it. In other words, we observe this universe precisely because it allows beings like us to exist. If gravity were much stronger, stars would burn out in seconds. If weaker, no stars would ever form. The fact that we find ourselves in a universe with the right balance is not surprising, because only such a universe can contain observers capable of asking why. At first glance, this seems like circular reasoning, but it carries profound implications. If the laws of physics can take many forms, then perhaps countless universes exist, each with different constants and dimensions. In this multiverse, gravity's weakness might be one possibility among many, and we simply inhabit the universe where it happens to allow life. This does not solve the puzzle so much as move it outward. The mystery of fine-tuning becomes the mystery of why such a multiverse exists at all. The idea of a multiverse is controversial. It arises naturally from theories like cosmic inflation and string theory, where the equations permit countless vacuum states. Each pocket of space could expand with its own physical constants, forming a separate universe within a larger cosmic landscape. If this is true, then our universe is just one bubble among trillions, floating in an eternal sea of creation. In most of those universes, gravity might be too strong or too weak, atoms might not form, and time itself might behave differently. We live in the one where everything aligns. But even if this cosmic lottery exists, the question remains, what determines the underlying rules that allow any universe at all? Why does existence have the capacity for variation? Why does mathematics produce realities instead of abstractions? These questions move beyond physics into the philosophy of being, yet physicists cannot ignore them. The search for deeper physics is, at its heart, a search for meaning in numbers. Some thinkers argue that fine-tuning may hint not at chance or design, but at a hidden principle, an unrecognized law that links all constants through geometry or symmetry. In certain formulations of string theory and loop quantum gravity, the strengths of forces are not independent at all, but emerge from the same geometric conditions. Gravity's weakness, then, might not be arbitrary. It could be the inevitable outcome of the universe's dimensional structure. The same geometry that gives rise to space-time might determine all the constants of nature. If such a unifying framework exists, it would render the apparent coincidences of fine-tuning inevitable. The values of the constants would not need to be chosen, they would be required by the mathematics itself. The universe would be self-consistent, its structure determined by necessity rather than chance. What we call fine-tuning might then be the expression of a deeper order, a symmetry hidden within the equations, waiting to be uncovered. Yet even this vision leaves us humbled, whether through symmetry, chance, or a cosmic principle beyond comprehension. The result is the same, a universe balanced so precisely that life can emerge to question it. Gravity's weakness is not an imperfection, but the key that allows time, matter, and awareness to exist. If it were any different, there would be no one to marvel at it, no consciousness to ponder the meaning of stars. Perhaps that is the deeper truth concealed within fine-tuning. The universe is not fragile by accident. It is fragile because fragility is the condition for creativity. A universe governed by overwhelming forces would be sterile and brief. Ours, governed by gentle gravity and subtle balance, allows the slow unfolding of complexity and the rise of minds capable of understanding it. The question that remains is whether this balance is the result of cosmic luck or deeper physics yet undiscovered. Every equation written by human hands, every particle discovered in the depths of space, brings us closer to the answer. But for now, the weakness of gravity stands as both a mystery and a gift, the delicate thread upon which the tapestry of existence hangs. And so, the story returns to where it began, the faintest of forces holding the greatest of meanings. Gravity may be weak, but its weakness is the reason we are here. It is the quiet constant that allows stars to shine, atoms to persist, and time to unfold. In its subtlety lies the very possibility of being. From the first spark of creation to the slow death of stars, gravity has been the silent hand guiding the universe. It is the faint whisper that became a cosmic symphony, the weakest of all forces, yet the most enduring. Across billions of years, it has sculpted light into galaxies, dust into worlds, and chaos into order. Every movement of every planet, every flicker of a distant sun follows its rhythm. It is invisible, unbroken, and eternal. At the beginning of time, gravity was there, shaping the newborn cosmos as it expanded from the hot, dense fireball of the Big Bang. The tiniest fluctuations in energy, magnified by inflation, became the seeds of all structure. Gravity took those seeds and nurtured them, gathering matter into clusters, stars, and galaxies. It worked patiently, without violence, using time itself as its instrument. The universe became a tapestry woven from its invisible threads. Through Einstein, we learned that gravity is not a force in the ordinary sense, but the geometry of space-time, responding to mass and energy. Matter tells space how to curve, and space tells matter how to move. The planets do not circle the sun because they are pulled by invisible strings, but because the sun bends space-time around it, and the planets follow that curvature, like ripples in a vast sea. Time itself slows near great masses, revealing that gravity is not only the shaper of space, but the keeper of time. Through quantum theory, we came to see that this curvature might arise from the smallest units of information, woven together in a network of entanglement. Gravity, in this view, is the harmony of quantum geometry, the collective whisper of the universe's smallest parts. The graviton, the hypothetical messenger of the gravitational field, may never be caught, because gravity is not a single particle's act. It is the conversation of all existence. Through the search for unification, we glimpse deeper patterns, extra dimensions curling beyond perception, hidden symmetries that link the forces, and mathematical dualities that make gravity and quantum mechanics mirror each other. Each discovery brings us closer to a vision of reality as a single, self-consistent whole, a universe where the weakness of gravity is not a flaw, but a necessity born from the structure of everything. And through the observation of the cosmos itself, we learned that gravity's reach extends beyond the visible. It binds galaxies through dark matter, sculpts cosmic filaments across the void, and communicates with the unknown substance we call dark energy. These mysteries do not diminish gravity's role, they amplify it. Gravity is the only force that speaks fluently to both the known and the unseen, the luminous and the dark. On the smallest scales, its restraint allows stability. If gravity were stronger, stars would burn too fast, collapsing into black holes before life could form. If weaker, galaxies would never coalesce. Every breath of air, every orbit, every moment of consciousness is possible only because gravity is so gentle. It is the universe's quiet tuning fork, keeping creation in balance. Its influence reaches beyond physics. It shapes philosophy and wonder alike. For millennia, humans have looked to the heavens and felt its pull not only as a physical force, but as a metaphor for connection. It reminds us that nothing exists in isolation. Every atom on Earth is linked to every star in the sky through the same curvature of space-time. The fall of an apple and the orbit of a planet are governed by one principle. In that unity lies a profound truth. We are part of the same equation as the cosmos itself. Perhaps that is why gravity feels different from other forces. It is not confined to laboratories or equations. It is felt in the motion of tides, the shape of mountains, the beating of time itself. It is the quiet music of the universe, always present, always patient. It has no opposite, no cancellation, no end. Where electromagnetism alternates between attraction and repulsion, gravity only unites. It gathers, binds, and sustains. It is the cosmic will to coherence. And so, the puzzle that began as a question of weakness becomes an answer about strength. Gravity's faintness allows the universe to last, to evolve, to think. It is not a failed force, but the condition for everything that follows. Its subtlety is its triumph. The paperclip lifted by a magnet still obeys gravity. The magnet's power fades with distance, but gravity's hold never does. Across billions of light years, through dark matter halos and expanding space, it continues to weave structure and meaning. Humanity's search for a theory of everything is, in truth, a search to understand gravity fully, to unite the quantum with the cosmic, the fleeting with the infinite. Every particle accelerator, every telescope, every equation carved into chalk is a step toward that unity. Whether the answer lies in strings, loops, or dimensions yet unseen, it will reveal that gravity was never truly weak. It was simply vast spread across the totality of existence. The final irony is that gravity, though invisible, is the one thing that gives form to all things. It holds the stars together and bends the path of light. It defines time's direction and gives matter a stage to exist upon. Without it, there would be no curvature, no history, no structure, no life. As the universe continues to expand into its distant future, gravity will remain its silent witness. Galaxies will drift apart, stars will fade, and black holes will evaporate into the darkness of Hawking radiation. Yet even then, gravity's story will not end. It will live on in the geometry of space, in the quiet persistence of curvature, in the memory of the structure it once shaped. And in that final silence, one truth will remain. Gravity may be the weakest force, but it binds everything that ever was or will be. It unites the smallest particle with the largest galaxy. It links the birth of time to the edge of eternity. It is not merely a force, it is the framework of reality, the pulse of the cosmos, the thread that weaves existence together. Perhaps that is the universe's final secret. Strength is not always found in power. Sometimes it lies in endurance, in unity, in patience. Gravity's weakness is the universe's greatest strength, the quiet miracle that allows everything to be.